Oh, it's okay. Okay, so today we have a half day, and then there's no lunch, so only for a few people. Okay, so this morning we're going to address and start to look at proponent models in terms of GMPs that are not developed by the Peer NGEs program. So there's a series of presentations on that. The first one is with Bob Young, and he's going to review the EPRI 2004-2006 review project models, which is a suite of models already aggregated into a model. And then we'll look at two other proponent models. We'll not completely finished. One is not completely finished, but just to get ahead and have the information so that when we come back in October with new models, I've seen them and you kind of know where we're going with this. Okay, so let's start with Bob Young. Oh.
What? Acting as resource. I'm always acting. So, at least that's what I'm supposed to be, a resource, I think. Anyway, so I'm going to summarize, I won't mention what I call this, but a summary of the EPRI 2004-2006 review project, which is the date of 2013. So there was a list of questions from the TI team, which are up in front here, and I will go through these as I go through the talk. So I guess the starting point, Norm described this briefly yesterday, and I will do it again briefly, but I needed to sort of set the setting for the review project. EPRI 2004 may have been the first official SHAC Level 3 study that was conducted, and I could say this was a far cry from SHAC Level 3 studies now, but we were learning in the process. So it was a model to characterize ground motions in the central and eastern United States, and it was done primarily for application in the new round of COLAs and ESPs, or that's basically applications for new power plants. They wanted to update the ground motion models for use with those assessments. So it was built on consideration of the available GMPEs. It developed a weighting scheme involving two steps. First was to group the available models into clusters, which were based on the modeling approach, basically single corner stochastic, double corner stochastic hybrid, and finite fault, which is how we grouped the models at that time. It weighted the models within the clusters based primarily on how well they fit the available data, and then they weighted the clusters relative to each other, mostly on the basis of what we called scientific principles, scientific merit, basically the underlying principles behind the models that were in the cluster. And for each cluster, we fit a weighted median model prediction to the member of the GMPs with a single form. Essentially, it was a backbone model that represented each cluster, and then developed epistemic uncertainty models for each cluster, which combined the effects of the model-to-model variability with estimates of additional uncertainty coming from other factors. And we represented then that uncertainty within each cluster by a 5th percentile and a 95th percentile model, and would fit that two models also with the backbone curve. So each cluster had three curves in it, a central model and a plus or minus model that represented the epistemic uncertainty, and then the four clusters in combination represented the overall epistemic uncertainty in the median. And the aleatory model was built from the range of aleatory models that were associated with those CEUS or CE North America GMPEs. And then EPRI in 2006 performed a SHAC Level 2 review study of just the aleatory model, And that conclusion of that study was that there was no compelling reason to think that there was a major difference in the alliatory variability between active tectonic regions and the Central Eastern North America. So it developed an alliatory model making minor adjustments to the preliminary alliatory variability from the NGA project that was ongoing at the same time. So these were preliminary results available in 1995, 1996 timeframe. So that set of models, the EPRI 2004 medium models and the 2006 alliatory models, became the sort of standard set that were used for all recent applications for power plants in the eastern United States. So then we come to the EPRI 2004-2006 review project. And this was motivated because significant time had passed since the development of the EPRI 2004 study. In fact, many of the models that were being used in EPRI 2004 had been updated or replaced, or were considered no longer supported by their original developers. So there was basically a lot of modeling work had been gone on in that approximately decade since the 2004 study had been completed. It was really actually completed in 2003. And there were a number of recordings of medium to moderate-sized earthquakes in eastern North America, so there was a lot more data to look at. So the evaluation was that there was a need to consider this new information, especially in response to develop responses to NRC requests for information, basically coming out of the task force on looking at the Fukushima accident, and the realization that we wanted to get that information into the assessment in a very short time frame before the completion of NGA East project. So this was designed to be an interim study, just to gather the new information, to basically be a refinement of the EPRI 2004 model, with the idea that NGA East would be the replacement of and then in the new guidance, the refinement models can be done basically at a SHAC level 2 level, and the replacements have to be up to the level of SHAC level 3. So it was done with the understanding that it would be replaced in the long term by the NGA East project, but it would gather this significant information that had gone on post EPRI 2004 to use that information for answering these letters in the short term. So it was conducted as a SHAC level 2 project, but it had workshops and a very active and large PPRP. There was a TI lead. Gabriel was the lead. Martin Chapman and I were on the team. As a part of the structure of the project, it was, as it being a SHAC level 2, it was decided that to make this more streamlined for the purpose of gathering and implementing, and also for the review process, that we would stick strictly to or as much as possible to the framework of EPRI 2004, 2006, rather than starting over and doing a whole new process, which NGA East was doing, and that would be the replacement. So it was sticking with the guidelines, so basically followed with the same concept of grouping the available GMPEs into clusters, using empirical data to weight the models within clusters, and making some judgment on how to weight the clusters. And that we would update the alliatory model with the final versions of NGA West Project 1 and what it was available at the time from NGA West 2. So the questions from the first question was summarize existing Central and Eastern North America GMPs as they have been assessed by the EPRI 2004-2006 review project. So this is the list of, this table is the list of models, in the printed models with the models that were used in EPRI 2004 and grouped into the 4 clusters. And the number of the models have been replaced by newer models. Some of them were no longer felt to be an adequate representation. A number of the hybrid models that have been developed that were used in EPRI 2004 were sort of very interim or embryonic hybrid models. The only one that was well developed was the Campbell hybrid model, or an earlier version of I think at that point it wasn't quite published, but we had access to from Ken to that model. So a number of these models have been superseded by newer models or felt that they were no longer valid. So basically we went through a process of looking at what the newer models and the basic 4 newer versions of, or new models that were considered were first in alphabetical order. The Atkinson 2008 referenced empirical model with the 2011 revisions. So it was at that time called A08 prime. And this basically is a model that it might be considered a hybrid, although some question, it's not a classic hybrid in the sense of Campbell 2003 hybrid. It basically takes a Western U.S. or an active tectonic region GMPE, calculates the misfit between that GMPE and a set of residuals, empirical data from the East, and then fits the model to those residuals to create an adjustment factor. So it's a purely empirically based adjustment factor model for the Central and Eastern North America. So it does that instead of what might be called the classic hybrid now, where you actually take the underlying model is still the same, a Western model, but then you use seismologic models to develop the adjustment factors rather than empirical data. The second model, which was a new model, was the Atkinson and Bohr 2006 with the 2011 revisions. So we have AB06 prime. And this was basically considered to be a replacement for the Atkinson and Bohr 1995, which was a double corner stochastic point source model. It used finite fault simulations rather than point source to estimate that, and then it had been adjusted in 2011 by Gail and Dave. The third model was the Pasesk et al. 2011 hybrid model. This hybrid model was constructed in basically the same approach that Ken originally developed, but it was built on much newer and better Western models. It was built on NGA West 1 ground motion models, and then used the same concepts of using stochastic point source simulations and techniques to develop the adjustment factors to go from active regions to the Eastern North America. And we consider this to be a replacement of Campbell 2003 and of Tavakali and Pasesk 2005 primarily because it used a much better set of Western U.S. ground motion models that had gone through the entire NGA process. And the final model, which was basically pretty much a holdover from the original model, was the Silva et al. 2003, which had very minor adjustments to the Silva 2002 model, and it was a point source stochastic model, and it had 1 and 2 corner components. And we dropped a couple of the Silva had, I think 4 point single corners and 2 double corners, and I think we reduced it to 2 single corners and 1 double corner out of the set because we finally got him to say which one he preferred. So that's the basic basis of the new GMPs that we added into the mix and why we replaced a bunch of the models that were there before. We also, in the process, we needed to, we looked at the clusters. The clusters before were based primarily on how the models were developed, which was stochastic singles, stochastic double, hybrid, and finite fault simulations. And that didn't quite work as well in the second round, partly because, for instance, is the AB06 prime is not really a pure double corner point source stochastic. It's finite fault. It may have some double corner-like behavior because of the simulations, but it's whatever the simulations produce is the source model. So it can't really call it strictly a double corner stochastic point source model. And whether A08 prime is a hybrid in the same form as the others is the question. So and the other issue, the issue that came out in our review was that if we put some of these models together in the sort of way we had before, we had models in 2 clusters that had 2 models. We have a model in cluster 2 that had 1.3 near source attenuation, and a model in cluster 2 that had one near source, a slope of 1. And that produced a very large difference in the estimates at 50 to 100 kilometers, and we had the same thing in cluster 3. So we basically had a huge epistemic uncertainty in the cluster, which just came from the geometric spreading. So we felt it may be more logical to group these models by the geometric spreading approach rather than how they were developed, because the underlying principle was really the geometric spreading that was driving the differences. So we redefined the clusters. Basically, the single corner clusters had those 4 models in there, although we treated the 2 Silva models essentially one model in the terms of how they were weighted in the model. So we didn't get double weight for showing up twice. We had the complex source, empirical source we called it, with 1 over r geometric spreading in the first 170 kilometers. So that went with the A08 prime model, which was basically how it was constructed, and the Silva et al. Double corner model. And then the 2, what we call complex empirical source, R1.3 models were AB06 prime and Pazesk et al. 2011. And then Somerville et al. 2001 survived because no one had developed a new model. We asked Paul, and he said, I haven't had a chance to do it, or no one funded me, or something like that. But anyway, we had no update to that model. And Rob was busy doing something else. So that model survived as cluster 4. So this is the basis for how we constructed the clusters. So how well are they constrained? So the simulation-based models are constrained by the simulations. And so in terms of the actual fit to the models, they're very well constrained. But then the question is, how well are the simulations constrained? And we went through the issue, yes, of calibration. They're calibrated primarily against empirical data, and that empirical data is an active region. So they were no better calibrated then than they are now. The hybrid models are built on well-constrained empirical models, and the assumption that they have the correct way to go from the west to the east. So that is the underlying empirical models are reasonably well constrained based on, especially the NGA set had a lot of data, but then it's just a question of how well those models, the understanding of what should be changed to go from west to east. And the referenced empirical is, again, built on well-constrained empirical models from the west, and then the adjustments are fit from the CE North American data, which, as we saw yesterday, is not primarily in the magnitude and distance range of interest to our hazard assessment. So if the models that were built in the west work well over the entire magnitude range, down to the magnitude range where the CE North America data is, and the adjustments are appropriate down there for smaller magnitudes, are appropriate at the larger magnitudes, they're well constrained. So it's the best I can do with that. So then the process we used for weighting the models, I want to emphasize that we had a tremendous amount of good cooperation with the NGA East project, and we stole as much as we could from them to do our short-term analysis. So we worked with an initial version of the NGA East database. We started with a February version, then we finished up with the August 2012 version. We took that data set and we were focused on developing ground motions for hard rock. That was the emphasis of our study. So we wanted to look at, quote, rock site data. So we took the data set and some sites had measured VS30, a limited number. The EPRI 2000, the study itself actually funded a measurement at, I can't remember, a dozen sites? 35. Anyway, a number of sites. So we went out and gathered more data of additional sites to add to the information on velocities. And then we used the information in the data set to classify the sites into 3 basic geologic classes. We defined a soft rock class, which was basically younger and softer rocks, intermediate rock class, and then class where the rocks are probably close to hard rock. So that was our empirical classification of the sites, and then we added we had sites with actually velocity measurements. And this is the data range of the data we used, and shown by the color-coded or symbol-coded by the classification. So this is a subset of the NGA East data set. We did not use anything that was classified as soil in this assessment because we wouldn't want to deal with the corrections from soil. We did something in that project that was not really done in EPRI 2004, which was to develop an adjustment from the site class recording conditions to the reference rock conditions. So we developed two sets of adjustments. One was an analytical adjustment for those sites where we actually had velocity data, where we can use that data to estimate how we would translate that site's response into hard rock. It was based on the quarter wavelength method combined with differences in the kappa estimate and incorporated uncertainty in VS and in kappa in calculating the adjustment factors. And then we also, because as we know that's the number of sites with measurements is pretty small, we wanted to use that empirical data. We also looked at an empirical adjustment where we calculated adjustment factors for the gross site classifications. Basically, we would use what we called hard rock as the reference condition, and then calculate adjustment factors for the other two classes, intermediate and soft. Unfortunately, because of the amount of data and the scatter, we can only statistically distinguish between soft rock and the grouped intermediate and hard rock groupings. So basically, that was this came out of our ability to differentiate that data, and it partly could be problems with misclassification because we just worked off of the classifications that listed in the database, which in most cases were coming from looking at maps, and as opposed to actually being there. So this is a comparison of the empirical adjustment factors versus the analytical factors computed for a number of sites at 1 hertz, and they look pretty good. The blue lines, the blue symbols with their error bars are the analytical adjustments for individual sites, and the uncertainty on those adjustments due to the uncertainty of velocity and kappa. And the red line is basically the base case became intermediate and hard rock in our analysis, and then with an adjustment to soft rock. And you can see then the error bar on the uncertainty for the plus or minus error bar on the soft rock adjustment factor at 1 hertz. At 10 hertz, it doesn't look quite as good because there's a shift. And the shift is coming primarily because we can't really distinguish in the range of intermediate to hard rock. We could not see a difference in the data set we had, but there must be a significant effect of kappa going on at this frequency. So the adjustments are all, analytical ones are all shifted off because our basic median set of adjustments are for a site that's got probably in the 1,500 or 1,300 meters per second. It's probably the average velocity of our sites if we had velocities for them. So if you shift those red curves up to where the red line is up here, then the adjustment factors look better in comparison with the analytical. But it was a
Can you go quickly over that again? I understand your line. What's going on the second plot? Yes.
On this plot. So this is analytical adjustments from the measured VS30 and kappa out to this point here, the velocity here. And so it has a nice decay as you approach that velocity. The adjustment goes to 1. For the empirical model, we can't see any difference in the data that we had all the way across that huge range of velocity. So our data set is mostly clustered down here. The mean VS30 is probably in this range. So this number here, this adjustment from here to soft, really is coming from there to there. So if you shifted the red curves up so that this line was about here, then it would look better. Not great, but better. No. we did not do that, but just in terms of the comparison of how well those two techniques used. And so we basically, felt that the analytical approach, the empirical approach was giving us a gross assessment of how to deal with soft rock versus hard rock, intermediate rock, but we couldn't really distinguish the differences in the intermediate and hard rock with the data we had. So within cluster weights, we were based again on the residuals between the data and the model predictions from the individual models within a cluster. And in those calculating those weights, we counted for the within-event correlation, typical tau and phi splits. We accounted for the uncertainty in the soil correction, which is correlated across site and individual sites. And we developed weights based on magnitude and distance bends to account for where we basically what we wanted to use to drive the assessment. And the fact that we had sensitivity and sample size. We didn't want, even though we made downweight a certain region, we wanted that a region may still have a lot more data than a region of more interest, and we wanted to account for. We didn't want, even though it was downweighted because of importance, it still may overwhelm the weights because of the sample size. So we made additional adjustments for that. Basically, we calculated the within cluster weights based on likelihoods, with a variance matrix built out of the factor of the correlations in the data set, which we thought was a little more flexible and maybe a little less ad hoc than what EPRI did. We always try to do something a little better. And basically, the covariance matrix was built like this. We have the tau, which is the event correlation. We have phi across sites. So basically, the same site appearing twice in different earthquakes is now correlated across that. So the variance matrix has that cross correlation. And then we have an additional uncertainty for each site correction, which is built into that assessment. And for the analytical corrections, we have direct estimates for each site in terms of the uncertainty and the assessment of the correction for the site condition. And for the empirical correction technique, we have all the sites that were soft rock had an uncertainty in the assessment, which is the uncertainty in the soft rock factor. So we built up this covariance matrix that has these cross correlation terms in it to calculate the weights. And then this is the weighting we did on magnitude and distances. We went down to magnitudes basically 4 or 3.75 with an emphasis that we would ideally like to have our weights based more on the data in the 5 range. So we had some downweighting of the clusters based on importance, and we adjusted those depending on whether we're looking at high frequency or low frequency ranges. And the distance range changed also as a function of frequency. So we used then calculated weights on the individual models within the cluster to calculate the cluster median model. And then we developed assessments of the epistemic uncertainty within each cluster. We used then an envelope of the model-to-model variability within the cluster based on the weighted combination of models, plus an assessment, independent assessment, quote, independent assessment of what the uncertainty in the cluster values would be. And we considered those to be basically two different ways of assessing uncertainty, so we took the envelope of those for our within cluster uncertainty. This is an example of, in cluster 2, of the model-to-model variability. Cluster 2, again, was the A08 prime and the Sobel double corner predictions. Both models being driven basically by 1/r geometric spreading in close. And we smoothed out, and so there are a lot of variations in the model-to-model, especially when you only have a couple of models. So we smoothed those across the distance range so that we wouldn't get a lot of oscillations in to get basically trends in how the model uncertainty weights. So our uncertainty model within cluster uncertainty varies with magnitude and distance. So we're not just doing a a simple shift of the backbone curve, we're actually fitting, we actually calculate fifth percentiles across magnitude and distances across the entire range and then fit models to those. So it's a little different than a simple backbone shift. And this is an example for, so that was probably that cluster, it was had the most within cluster variability, and then cluster 3 had one of the smallest, well, not the smallest was cluster 4 since it only has one model, but cluster 3 had the predictions between the A08 prime and Pozesk et al. Are actually very close over a wide distance and magnitude range. Even though one of them is a finite fault, the stochastic simulation, and the other one is a hybrid, they're both being driven by the same sort of geometric spreading model, and that's controlling basically the result. So the independent assessment of independent cluster, we started out with the NGA East, basically providing us an estimate of how well we have, basically the amount of data we have gives us some idea of how well we can empirically constrain a ground motion prediction equation. And we originally started using this at basically for all magnitudes, but then with some very strong recommendations from our PPRP, we basically felt that we came to the conclusion that was really constrained at about magnitude 5. And we needed to build in additional epistemic uncertainty for scaling from 5s up to the magnitudes of interest. So we basically built a cluster-independent epistemic model that was a combination of the database estimate at 5 and then this additional magnitude scaling uncertainty. So the magnitude scaling uncertainty was basically constructed by looking at how the magnitude scaling in all the relationships we had to look at. So we looked at the variability in the amplitude at some magnitude above 5 divided by the magnitude at 5, the values at 5, look at that variability across the entire set of models, and then we evaluated that and then looked how it went across our median models to develop an estimate for what it looked like within the clusters. So this is a plot of basically the scaling from magnitude 5 to magnitude 8, predicted by each of the models we considered. So what's plotted here on the horizontal axis is magnitude, and the vertical axis is ground motion at magnitude x divided by the ground motion at magnitude 5. And it's done for, this is 10 hertz, and it's done for a range of distances from 1 to 500 kilometers. So each line is a different model. So the red line is A08 prime. So the red line down in this case, this is basically coming from, you're in very close. The empirical models have nearly full saturation. So there's not much magnitude scaling at 1 kilometer from NGA West 1. And as you get to large distances, there is. So this is basically at different distances how the magnitude scaling looks across those however many, 8, 11, 10 models. So the variability at each of those distances can be computed. So this is the standard deviation in the amplitude, the ratio of the amplitude at magnitude m versus the value at magnitude 5 across those models. And we looked at this and said that looks reasonably well behaved, that we could represent it by a relatively simple linear relationship, that the standard deviation goes up with magnitude according to a factor of about 0.3 at magnitude 8 versus, so we have a sigma in magnitude scaling of about 0.3 at magnitude 8. The ratio of the amplitude at 8 to the amplitude at 5 has a standard deviation of 0.3 in log space.
Bob, again, real Fortuletta, what are the different boxes again?
Different distances.
Okay. So
1,
the upper
5, 10, so 1, 5, 10, 20, 30, 50, 70, 100, 140, 200, 300, 500. This is all for hertz. Actually, all the periods are on here. Sorry. So the plot shown here has all the periods, PGA to 0.5 hertz by color.
Can you go back to
This.
Yeah. Okay. So this is 10 hertz.
This is 10 hertz. This is just the ratio of the prediction at 5 kilometers of A08 prime of magnitude 8 divided by his prediction at magnitude 5.
But that's coming out of the models.
Coming out of the models themselves,
okay.
the individual GMPs.
Okay. Good. Thank you.
So you take all of that and you can collapse that into this figure for all 7 or PGA in the 6 periods. And they behave basically very similarly in terms of cross periods, and we can represent that uncertainty we represented it anyway by a linear model that just said the uncertainty in magnitude scaling is just a linear function of magnitude. It goes from 0 at 5 because we're starting with 5 and increases to about 0.3 or so at 7. I mean at 8.
And that applies at all distances.
And it applies at all distances.
Okay, simple.
There are some variations. It gets to very large distances. That was coming probably, we felt, also from distance scaling factors, and we were really interested in the first 70 to, within the first 100 kilometers, and we felt that region could be represented reasonably by a linear model to first order.
If you go back one, most of that sigma there is from at least short distances from the A08 model, right?
They're very short distances, yes. As you move out to 10 to 30 kilometers, it comes up into the cloud.
Do you know why? Where's Gail? Now, do you know what's going on in her model that it's very strong saturation, right?
Yes, it's
saturation in the NGA model.
Saturation of Bohr BA08 at 1 kilometer.
And all those others with a steep slope are not saturating.
Are not saturating at very close distances because they're driven by a different underlying model. They're not really anchored that hard on Western models.
But all those point source models, the saturation depends on your effective distance correction.
Yes.
That's where it all comes in,
yes,
right?
It comes in the effective distance, right. The point source models, the finite fault model, A08 prime is, we know that we know that XM has, in close, it produces very big numbers, so it doesn't have much saturation in it.
Well, which one is the blue line?
Which blue?
One
light blue, dark blue?
Light.
Light blue is PCT, Possescadol. So that one, again, is lower, and it's driven by NGA in close, because it's the light blue one in here.
Bob, just one quick question. Were the hybrid models in there as well? Because they would presumably have shown the saturation.
The hybrid model is the Possescadol. It's the light blue in here. It has less saturation. It may be that, I don't know whether your model has more saturation than the composite NGAs. So, the Possescadol was built on the composite NGA, and A08 prime is built only on BA08.
They shouldn't be that different in their saturation. I thought that Possess model had a constant stress drop. Is that right? And so, whereas if you tried to invert the models, you would for those parameters, you would get a little decrease in stress drop at magnitude. I thought that's what was the different scaling. Did you apply constant stress drop? Magnitude independent stress drop?
We did have constant stress drop.
I thought if you try to invert everything, you would get a little bit of a decrease in stress drop, depending on how you do your effective distance, right?
Yeah. Ken Campbell. Yeah, I've looked at this, and in fact, in my talk, you'll see a comparison of the hybrid empirical models, and what you'll see is an A08 prime, and you can see this actually if you compare the BA08 model with the other models. It has a much stronger, let's say, it's much flatter as you get in close, and it has sort of much higher ground motions as you get out to about 30 kilometers. So what Bob said is right. If you compare those, it has significantly more apparent saturation to it than the other models.
Okay, so we wouldn't
and I think that's what you're seeing here.
If we had used a different model, you wouldn't have seen as much. Is that what you're saying?
And the reason SSHAC et al. Uses all four of the NG models, so it doesn't weight the BA08 model as heavily as A08 prime does, which gives it 100% weight.
You done staring at it? No.
But on the next one, you used the constant overall distances, so it's really like your 30-kilometer range, right?
Yeah. But we did not really use the 1 kilometer number. We just took a relative constant that was representative of the distance range of primary interest. Because, I mean, although we would like the models to work for magnitude 8 at 1 kilometer, we have very few sites where that's really an important calculation for hazard evaluation. So we built a model that basically represented this into a first approximation by a linear increase in the magnitude scaling with magnitude. And we then RSS that variance as with a function of magnitude with the data-based uncertainty at magnitude 5 to produce an overall estimate of the variability with magnitude. So this just showed total across all models, and then when we went down to cluster variability, it got a little smaller, so we were looking for trying to get the within cluster uncertainty. And we built then from that because the cluster variability is going to be carried across by, we have models for all 4 clusters with weights. So this is our cluster independent epistemic uncertainty, which has a distance trend and a magnitude trend.
Ralph Archuleta, can you go back to that previous slide? What is the hinge there at between, let's say, at magnitude 6? There looks like there's a break. In other words, it goes convex above that, but then it's of the opposite convexity.
The way the models behave at different magnitude ranges, and as you get out to large distances. You just have to go into the details of how they all scale and with distance and magnitude.
I will say this is a norm. I have to say every time. No. Okay. But that's implying, let's say, that yellow line or where it's coming down at 1 hertz at 50 kilometers, right in the middle. I think you're getting that where there's a break and it's coming down. Yeah. The models happen to all be scaling really similar with magnitude over that magnitude range, right? And as you go below it or above it, it's less.
Yeah.
If we were talking about the West, I would understand that because that's where our data are, right? That's the center of the scaling, and we're going to the edges. But a lot of the point source models you think would be...
But that's true, but the point sources are mixing with the West, and so they're doing different things in different periods, and they just show up as... If they were all point sources, this probably would not look like this. But some of them are are stochastic models being extrapolated maybe down to 5. I mean, the simulations that were done for A08 prime or AB06 prime, I don't know, I mean, how much they've done simulation, whether that extrapolates down. So there's a mixture of stuff in here, and it just produces differences in scaling across this whole magnitude range.
Oh, another possible explanation, I'm not sure of that, I was trying to check the report, is remember that the Somerville model kicks in around 6.
Yes, but I think I used it all the way down.
You used it,
for
okay.
this.
Okay.
Because even though it never got any weight below 6, it behaved with no worse than many of the other models down there. So basically, we're seeing, finite fault simulations, 2 different kinds, mixed in with point source stochastic, double corner, single corner, with empirical hybrid models, and they're all built on different engines, and they're all just behaving a little differently as we cross the magnitude range. And we just captured that in a gross sense with a linear model. And then basically, so we now have the red line here is our basic data constraint based on how much data we have. So we have a lot of data around beyond 100 kilometers, so that's where empirically we have the best constraint on the data in the east, and then it goes up with distance, both directions, strongest out at larger distances, and then we scale it up for magnitude effects. And then we take this envelope of this with the model-to-model variability to construct our within-model uncertainty. And for model cluster 2, where we have quite a large scatter, as you saw from the very wiggly lines, this is the envelope curve smoothed out and we capped the uncertainty at 500 kilometers. We didn't let it get any bigger because we couldn't get the model, derive a good fit to the data beyond if we did it blow up. We started to curve back. So we just capped it at a very large number. And if we go to cluster 3, it's basically very well behaved within the cluster. So quote independent uncertainty controls that model in terms of and cluster 4, of course, which has no uncertainty, there's only one model, or no model-to-model uncertainty, has basically this same uncertainty. And then the process was we take the median data, so we take the weighted median of the models within a cluster, and we fit a functional form to it. And this is an example of the fit to the medians for cluster 2. And then we calculate, given the median, then we have our plus or minus uncertainties. Epistemic uncertainty is a function of magnitude and distance, and we produce 5th percentile predictions at all distances and magnitudes, and fit those with the same functional form but new coefficients. And then we do the same for the 95th percentile model and fit those. And so in terms of the models, the functional form works very well, and it fits the predictions very well. So there's very little misfit in terms of fitting the prediction. So it's all driven by the epistemic uncertainty. So basically, the process is we have 4 sets of backbones. So basically, 12 backbone models. Each one a median for each cluster, and then a plus or minus on each cluster. They're all fit with similar form to represent the 5th and the 95th percentile of those things, and those differences are magnitude and distance dependent, and frequency. So that's the basic way the models were constructed.
But it is still like a backbone in the
yes.
scale, in that everything is up or everything is
is
down.
up, everything
There's
is
no
down.
crossing path.
There's no crossing. So there is difference in magnitude scaling across the frequencies and distance scaling, but it's all high. So it's the high magnitude and the less distance go together, and the low magnitude and the high distance. And so, if we go back to this figure here, the model-to-model variability figure, there's a lot of crossing going on in there, which we smoothed out. So we do lose that. We build in that strong correlation that it's always high for everything, or it's always low for everything, which is just the way that process works, unless you want to build a lot more models.
But we could have taken what you've got at these points for the median models and slapped on not just the sigma up and down, but a covariance matrix on the coefficients and generated models.
Yes.
Right.
Yeah, just one thought, something like what we're doing for Hanford.
Yes, for Hanford. So for the Hanford process, what we did here was we built a bivariate. We basically are using a bivariate Gaussian distribution for the scale factor and the magnitude scaling. So we have 9 models, and those models cross, and which is a very parametric version, stronger parametric version than what Nico's doing, where he has a full covariance matrix for everything, and he builds 15,000 models. So, questions from the team: what are the limitations of these GMPs? So, of course, the question we're wrestling with here is, have we captured the model space using that set of available published models? We have extended the model space because we've calculated a sigma from the models and then gone beyond that to some extent. We haven't really plotted the curve to show that we captured them all, but the sigma is, we calculated sigma from a set of models, and then we calculated 5th and 95th percentile. So on general cases, I would expect that's beyond most of the models over most of the distance ranges. And the other important limitation is we only did this for 7 frequencies. So the model is, because we were repeating the same 7 frequencies. And so you're stuck with, what do you do in between, and what do you do at longer distances? So that's basically a couple of limitations. I'm sure we can come up with many more, but it's basically driven by those 10 underlying models and representing that uncertainty.
But even for the limited range that you've got here, for those frequencies you have and distances, we take this, we can project those all onto the same Sammons map and see where they're falling.
Yeah, we can.
It'll all. I think we can incorporate it at least for checking and comparison.
Yes. In the application, everyone has developed interpolations across these models using the new reg CR6728 or something like that, but they're only, again, defined for these PGA and 6 frequencies.
How many are we committed to doing frequencies? Enough? Is that it? 23. All right.
Okay, so the next question was, what is the basis for the range of GMPs defining the project? Defining the epistemic uncertainty, and basically it was within cluster variation with an envelope of the data constrained at 5 and this model-to-model and the magnitude scaling uncertainty, which I went through. What is the distribution of magnitude, distance, sighted conditions, style of faulting, period range, for which the review projects are well constrained? So, as shown by the fits, the models fit this curve fitting, as Norm said yesterday. Once you have once you can define numbers with no variability across a wide magnitude and distance range, you can come up with a functional form in general that fits those very well with very little sigma. The sigma misfit is like 0.03 or something like that. For the median, it's very tiny, and the 5th and 95th is like 0.03 or 0.05, and not worth even bothering to worry about including. But to the extent that the underlying GMPs are constrained, then that's the underlying thing. So they were designed to be used for magnitudes above 4 and above, because there was a potential we would be doing CAV calculations, and they're designed for to go out to the data we used was out to about 300 kilometers. They're designed to go all the way out to 1,000. They're used all the way to 1,000. They're probably used beyond 1,000. So although everyone says we don't have to worry about it, I keep saying we need to make sure our models go out beyond 1,000 kilometers, so that we do not
in a reasonable way.
In a reasonable way, so that we do not overestimate ground motions from New Madrid at 1,500 kilometers, because people will be asked to check. And this is the how was the extrapolation done? Based on fitting the models, and the applicability is down below. Same, those 7 frequencies out to 1,000 kilometers. And is that it? That's it.
Thank you. I think we covered the easy, quick questions here, but we can go for one while we do the change of setup. Is there a microphone there for Larry? On your Larry is asking for a microphone. Ralph. So.
Larry Salamone, Joint Management Committee. My question is, and I'll share this information as a resource expert, very familiar with what was done for the EPRI 2013. One of the things before we published that I wanted to be sure of, there was also a body of work being generated by the USGS in the update of the National Seismic Hazard Maps. We all know the difference of the probability of exceedance range that they focus on, and the difference in the methodology, versus a SSHAC methodology like EPRI 2013 used. But as an engineering perspective, it's always good to kind of build off of the foundation of other new work as you move into the darkness of new research to improve the state of practice. My question is, if we think of the EPRI 2013 as a whole, as a proponent model, as well as perhaps the USGS updated model in 2014 as another proponent model, how can we best serve the NGAE's project as they go through the validation and the cross-checks?
So, I think the thing is that we will see where those models lie within what we're coming up with. In the process of see where they plot them on the SAMIS maps, make sure that they're being captured within the range of what we're generating. And if there are differences, we need to understand what's causing the differences.
As a point of information, too, we did that with USGS, and Mark Peterson has documented how close the results were in his documentation for the 2014 maps.
I think the key issue here is going to be where things are centered, because I expect we're going to get similar ranges to what Bob just described. But the centering all depends on the site conditions and taking that stuff out. And I am not at all convinced that any of the previous studies have dealt with all of these problems we're talking about in site conditions.
Yes. So we did not move the models to the sites, but they're offsets from the prediction equations, the prediction equations are all designed to be for hard rock. Right. So the offsets of the sites with respect to those prediction equations do influence the weights. And so the weights do influence the centering. So the site conditions do show up. We didn't move them to the sites, but they do influence the weights and which model gets higher weight.
Right, but that plot you had of the analytical calculations and the empirical and the misfit, that's part of the slop that we have to deal with. That's part of the slop.
And we averaged the weights from the analytical and the empirical fits, but we still have, it's clearer from that the data set at that time we were not able to distinguish sites that were hard versus sites that were intermediate, when clearly we would expect analytically there to be a difference across there. And it could be there was a lot of misclassification in there.
Okay, well, we have to move on. Next speaker is Chris Kramer with a performance model, recently developed model.
I'd like to start by giving you a little background on what we've been doing, looking at just the empirical data available for Eastern North America. Last summer, we basically used the NGA East database to develop an empirical model, which of course has magnitude level limitations, as you will see. This summer, we've been working on incorporating the intensity data, converting it to estimates of ground motion, and then using those estimates to see if we could try to better constrain at higher magnitudes. We're still kind of finishing up this summer's work, so this is sort of a progress report on that aspect. So basically what I'll be showing you is by combining intensity-based estimates of ground motion with the NGA East ground motion database, we can provide some observational coverage between magnitude 2.5 and magnitude 7.7 over a distance range of around 10 kilometers to not quite 2,000 kilometers. Not surprisingly, the intensity database estimates help constrain the empirical NGA GMPs at magnitudes greater than 6, although there is larger uncertainty involved. Acknowledgements, first of all, Norm in a casual conversation a couple of years ago mentioned, hey, we finally got enough data to be like California 3 decades ago, and it gave me the thought of, well, let's try looking at it at least to understand maybe a little better what the observational data is trying to tell us or what it can tell us, more than trying to develop a GMP that might be rigorously defendable. But it would be fun to try it. So, and we got a little support from the USGS particularly to develop the use of the intensity data into ground motion estimates and add that to the database and see how that might help our understanding of what's going on. Overview of the presentation is basically I'll cover the data sets used. I'll cover the empirical GMP development and then some results. Data sets used, particularly this summer, is the NJ East ground motion database from 2014, the ROD 55% damp file that has been provided. We've added to it that's wrong year, it's 2001, Bhuj, India, 5% damped observations from Kramer and Kumal, 2003, and we have used the geology-based VS30 estimate so we could have a VS30 term in our regressions this summer. That is going to be kind of a crude estimate. There'll be a lot of uncertainty associated with that. For the intensity observations from Eastern North America, and we basically for VS30, we've used the Walden Allen-based VS30 estimates, and basically there's an app online that you can use to get these estimates that Naeem has used to come up with estimates of VS30 at the intensity sites. This should be very familiar. This is the coverage of NGA East. It also, let's see, I got to use this to get the. It also has the Bhuj data set, which is out of NGA East, the Gosley, which is out of Eastern North America, I'm sorry, not NGA East, plus the Nahani data set above magnitude 6. When we add the intensity data, which is what we're interested in, we do get some filling in above magnitude 6 down to as close into 100 kilometers and a little bit closer in some cases for the Charleston intensity data set, Charleston 1886, and the 1925 Charlevoix earthquake at magnitude 6.2. So we're getting a little filling in here, still not enough at really close-in distances, but headed the right direction. So ground motion data selection, basically out of NGA East and also the data sets in the intensity data sets is to avoid the Gulf Coast for now. And of course, if we have any information from the crossing into western U.S., we avoid that. So we've selected data above 35 degrees north latitude and east of 100 degrees west longitude. And we've added the Nahanni, the Gosley, and the Bouge data observations. The Bouge data, of course, are engineering seismoscope data, so they're not actual records, but they give you good peak on the horizontal to work with.
Chris, one
Yeah.
quick question. Bouge data, was it free field?
Was it what?
Was that free field instrument?
Yes. So for the let me back up one thing. In adding the Bouge data, there are some concerns that at these large magnitudes, since it's contributing the most data that we're adding up there from actual observations, is the Bouge data appropriate to use directly in eastern North America? And we may have a partial answer to that from what we did this summer. Intensity data selection. We converted the ground motions, two ground motions from intensity using the Dankua and Kramer relations. There are a limited number of periods involved in that. We checked the conversion using the Saguenay and the Mineral Virginia observations to make sure that it looked like that this conversion was working pretty well. Then we reviewed the available magnitude greater than 5.6, and we did the median ground motion estimate versus median distance for that intensity. And this will become clearer in the following plots. And then ended up selecting the greater than magnitude 6 ground motions estimated from intensity observations to use in the inversion, or the regression, I should say. This is from Dankua and Kramer, and gives you some indication of what there are for PGA. We can both, the data sets are compatible between Western and Eastern North America, and these little air bars on here, which are kind of hard to see, easier to see here when we separate it out from the Atkinson and Kaka 2007 data points, are the 95% confidence level of the instruments estimates of the median ground motion at that intensity level. I've included the Bouge data. We included the Bouge data on the plot, but not included in the inversions. We get pretty good relationships up to high intensities on that data set. This is 1 second. As we get the longer period, including PGV, there is a separation between Eastern North America and Western North America data. We have less data in Eastern North America, and we can't go to as high intensities with confidence. And this difference is shown between the black line for Eastern North America and the light red line here for Western. And the data showing it is in the comparable color with 95% air bars. Again, the Bouge data is shown but not used. So there is some limitations at longer period on higher being able to use the higher intensities using this conversion.
the California data coming from the vault, or is separate?
That came from Atkinson and Kaka. They gave us their data set. So this is the check with using the Saguenay in the upper left corner. And for each intensity, we get boy, this is great fun. Yeah, there's a oh, it is working. It wasn't working before. Yes. Okay. Keep your hands off that pad, yes. Causes more headaches than it's worth. Okay, for each intensity, we came up with a median distance and median estimate of the ground motion from the relationship. And we've plotted that here in the blue symbols with the MMI values shown, plus the actual observations from the earthquake in the red. And we can see that particularly at larger intensities and where we have good observational data, they agree fairly well, giving us some confidence in what we're doing. At lower intensities where we may not be sampling the full intensity distribution in distance, particularly at intensity 2, there are more problems. We also don't have much data here. This is an MMI database for Saguenay. For a mineral earthquake, this is taken from Did You Feel It? So it's community internet intensity. There's a bit of difference between the two.
Chris?
Yeah.
Quick question. I'm not sure I can read the scale of the horizontal axis.
Oh,
it's distance times
it's
what?
distance in hundreds of kilometers.
Hundreds,
200. I was going to
okay.
point this out. I'm sorry.
No worries.
This goes out to basically 1,000 kilometers. This is PGA in units of G. And it's the same thing on this plot here. Here, again, we show just the conversion using Dankua and Kramer. This is for PGA. And it does, again, pretty well at the higher intensities. Lower intensities, it may be due to distance sampling. We're not getting the median distance quite so well and not doing quite so well. But it's encouraging that this may have some value. Historical earthquake magnitude.
Before you go,
yes.
My understanding is that as part of source characterization, some intensity data were collected for Central Eastern North America?
Yeah, we've collected the data. No, we collected it ourselves from published information.
If somehow.
And you know, there's also the NOAA data set, but we've gone for these individual events to the original papers that presented the information.
I can answer Yosef's question. He's working with individual site intensities. The intensity data in the source characterization is maximum epicentral intensity.
That is a difference, yes.
I'm answering Yosef's question about the intensity data in the source characterization versus this intensity data. The intensity data in the source characterization that we collected was maximum epicentral intensity we use for magnitude estimation. And what he's working with are individual site intensities.
Okay, we need magnitudes for the historical earthquakes, particularly the magnitude 7s. For this study, we chose the results from Kramer and Boyd for the New Madrid main shocks in Charleston, the 7s. This is basically based at using the concept that the larger the magnitude of the earthquake, the further out it's going to be felt, that is mostly controlled by magnitude of the event, and then basically looking at the level of intensity averaged over 600 to 1,200 kilometers to come up with these estimates.
One comment, Chris. Have you compared these to the magnitudes in the CUSSSC catalog? Because I think for consistency within this project, it would be nice if they were, or almost required, that the same magnitude be used.
In fact, I think maybe using NGA East magnitude, because there are
they? I just heard a mumbling of not available. No, it's available, but
NGA East database, ground motion database, does not have recordings from the New Madrid 1811 earthquake in it. I was, but I didn't feel it here in California. So, yes, we have estimates of there's the central estimate of the magnitude of those events. I think Charleston is 7.
Yeah, I think Charleston is the least controversial of these magnitudes.
And the other ones
are close up and down.
They're close. They're within the ability to estimate moment magnitude now. Yeah. They're close.
This is a paper that's almost in press in BSSA, so I can provide you a preprint of it if you're interested. We estimated confidence limits, which are shown here, plus or minus 0.3 magnitude units is a 95% confidence level on these magnitude estimates. The historical earthquakes, probably a little less controversial as to magnitude because we have instrumental estimates from these sources for the Grand Banks, Charlevoix 25, and the Saguenay earthquake. What this plot shows is the various data sets above magnitude 5.6 with the year of the earthquake here, and this is plots connected by lines of the median estimate of PGA at the median distance, just to give you an idea of where the relative weight of these data sets are located. One of the 3 interesting things I'd like to point out, and I better do it with a mouse, not my finger, is here on the Mineral Virginia earthquake, where we had some evidence of direct activity in the northeast or increased observations in this distance range. It does seem to curve more strongly upward. The 1929, which is offshore, and we're missing a lot of data offshore, observations of intensity at near-end distances and biases the larger intensity median distance estimates, which is probably too far out. So these data are probably not particularly reliable for use in this, and only the really far out intensity information is probably reliable, and we ended up just using the data for these 2 intensity levels. A third interesting thing, and maybe some evidence for actual nonlinear soil behavior at large magnitudes, is this is a December 1811 New Madrid earthquake, and as we get close in, these points seem to drop. These are pretty much within the Mississippi embayment at less than 200 kilometers, or getting in there where we have a thick soil column and could have nonlinear effects. And it's crossing down below this line, 7 line from Charleston. Maybe it's evidence for nonlinear soil behavior. Nonetheless, we looked at our estimates of VS30, and these estimates are lower than these estimates out here. So this can carry some information about nonlinear soil behavior, if that's the cause, or what's going on at lower VS30s. So since we had a lot of data already up to magnitude 6, we dropped those data and retained the 1925 Charlevoix earthquake, Charleston, the 3 New Madrid earthquakes, and the Charleston, South Carolina earthquake for use in our estimates. Now I've been showing you the mean estimate versus the median, or the median estimate versus the median distance, which is this curve here. The actual observations actually, there's no uncertainty associated with the line, but the observations can provide uncertainty and carry it forward if we use these things as point estimates and converting them. And it also can get into a bit closer in distances. Again, there's be some increased uncertainty associated with this. And again, showing for the 1925 earthquake, this same sort of pattern. So we've actually used the point data, converted it to estimates of ground motion as ground motion. So empirical GMPE, things should move along fairly quickly now, shows something about the approach we used, the functional form, and some results. Basically, the approach is a two-stage regression of Joyner and Bohr, which tends to be used, which of course provides both between event and within event variability estimates, and it also gives us event and site terms, which can be useful. The form is basically, a function of distance and a function of magnitude, which is part of the two-stage. Again, we used log base 10. We could have used log base n. We can get back and forth pretty well, I think. This function is a function of distance. Does have a magnitude-dependent geometric spreading term in it. Naeem chose to use a reference distance of 1 kilometer and scale or ratio everything relative to that. And of course, we use a VS30 term we chose to start with 760 meter per second. This could be changed. We can calculate something else from this. It also gives the within event variability. This is the magnitude term. This is basically focal mechanism of we don't know, reverse, and strike slip, which also includes the few normal events that are involved. And these are just, if it's that, this is 1 and the rest are 0 type switches. And then again, magnitude and magnitude square dependence and the between event uncertainty or variability. Standard form for what R is here, except we're using epicentral distance to start with in our inversions. We could not fix the pseudo depth term, or could not invert for the pseudo depth term, and wasn't very sensitive. The results weren't very sensitive, so it was fixed at 10 kilometers. And of course, this is the standard relation for the total sigma to the between and within. So as to results, I can show you a little bit of the GMP observations, sigma comparisons. This isn't the right version. I'm not going to do comparisons with it because I'm running out of time, and I removed it. And some single station. This is comparison up near magnitude 6, magnitude 5.9 is the curve from the regression this summer. Basically, there are 3 events shown here, Saguenay, Mineral, and then the Charlevoix intensity data, which shows the greater scatter of that data and shows you some of the fit. We've also compared last summer's intensity, ground motion only with ground motion plus intensity observations with some comparisons at a magnitude 7.6 and this time 5.7. Basically, for at the larger magnitude level, orange dots are the Bouge data, which were available for PGA, and this is intensity data, the other colors. Similar results with a little lowering of the estimates closer in, not controlled by a whole lot. That's less than 10 kilometers. Where we have a lot of intensity data, just looking at the available stuff, the Oklahoma, Mineral, and Saguenay, we see what it looks like against not much change going on. The intensity data is influencing where we have a lot of ground motion data constraining at lower magnitudes. I was going to show you more. I'm sorry, I got the wrong presentation here. Not the one I revised last night. I thought I downloaded. I apologize. We can go over this later if you're really interested. I did some sigma comparisons. This basically at what we have available, both without intensity and with intensity regressions. Again, basically what's showing up here, particularly within event, we're getting larger variability. Between event, it's about the same, except maybe at 1 second. And of course, the total, has larger variability associated with it. This I don't want to talk about. We did some single station estimates.
Chris, do you have magnitude scaling?
Sorry, what?
Do you have magnitude scaling of your model? Your PGA versus magnitude, for example?
Plot of it, we can do that, I'm sure.
I was curious at large magnitude.
In showing you, I'm sorry, I got the wrong one. I was going to show you at 0.3 PGV in 1 second. Basically, our differences are bigger at longer period between when we add the intensity data because there's less control from the actual ground motion observations there, and it tends to give you lower estimates closer in. So that would change some of the magnitude scaling, and that's one of the problems we're trying to finalize here. I don't have the magnitude scaling directly, I don't think, right now. But we did some single station just because we could do it. This is based just on the ground motion at real observations. Again, basically, not surprisingly, and I think others have done this, we're probably getting similar results. For the single station, we're getting around 0.3. These are log base 10 units versus a total sigma from the regression above 0.4. These are from 31 averages from 31 stations with 30 or more observations.
This is Linda. The second column, is that VSS plus tau, the total single station?
That's the single station sigma. I'm not.
Okay. Not just
as defined by Gale, these results are very similar to what Gale found in Southern California in her original paper. So just to wrap this up for time's sake, combining intensity-based estimates of ground motion with the NJEAST database can provide some observational coverage up to magnitude 7.7 over a distant range from about 10 kilometers to close to 2,000 kilometers. The intensity-based estimates can help constrain empirical in Eastern North America GMPEs above magnitude 6, although with greater uncertainty, which isn't too surprising. Thank you.
I think, Chris, it's nice to see comparison with the other GMPs as well as the magnitude scale, just to make sure where we are.
Yeah, we're working on that. I didn't want to show it because we're still in process of trying to do that. It's one of the things we're trying to finish up. But it does, when we add the intensity data, it seems to fall within the same range of the other GMPEs, roughly speaking.
this is norm. You have to, I'm going to drive myself crazy saying that. You said those single station sigmas were similar to Gale's. Those are big numbers.
This is log base 10.
I know. So,
okay.
So 0.3 is a lot bigger than what we're finding.
Okay. But they are reduced from...
They're reduced.
They're reduced.
Yeah, I think that's what you...
Okay, maybe I misstated the comparison.
And your sigmas are there's no magnitude dependence in that, right? It's just whatever comes out?
Yep, right.
So this is dominated by the magnitude 4s.
4 to 6s, right.
Okay.
This is for smaller magnitudes. We have nothing above 6.
Okay, quick question on the, you say you used the flat file 2014, your flat file or our flat file?
Yours.
Okay, so do you...
For the more final VS30.
Okay, so that's what I was wondering. Okay, thank you.
Yeah, this is just a comment. You know, I think this is worthwhile to do, but of course you're necessarily constrained by the fact that there really is very little data at larger magnitudes and closer distances, and I think it's worth noting that for the magnitudes above about 5, 5.5, and distances inside 50 kilometers, the predictions are going to be largely controlled by the functional form.
Yep. I agree with that, and there isn't much data in there above 6 at all. I did some comparisons of the residuals relative to the NGA database, and of course it looks good up to about magnitude 6, but beyond that, you just have no control on it.
So, Chris, this is Ken Campbell. I noticed your functional form doesn't allow for, say, a MOHO bounce type of impact. Now, did you just not consider it, or you don't see it in the data that you're using?
It's not a case of not seeing it in the data. I'm not sure we have the data to see it. Most of the data is beyond 40 kilometers. We started purposely with a simple form. We can add in that, but as Gail showed yesterday afternoon and in previous ones, that the functional form, particularly if you don't have a lot of data control, isn't overly critical. But again, we purposely started with a simpler form, and as needed, we can make it add a bilinear or something like that. But we purposely started with linear because it didn't look like we had much control in the range where that would be more important.
This is Gail. In PGA, which is what you were plotting there, you won't see any need for anything other than a linear form. I think the only place you're going to see that is when you look at lower frequencies. I don't know whether you've looked at lower frequencies yet.
We looked at PGV and 1 second. There are some problems with the Bouge data at 1 second. Being imported, it may not behave, it may not have the intermediate spectral sag to it. It seems to plot high, so that's something to be considered, whether you include that data or not, particularly at long period, and we're just, and that's going to influence what we actually put in the final results.
Okay. Chris, so I asked Chris for magnitude scaling, and it's nice to see comparison also with the other GMPs, and then also scaling with VS30.
Yeah.
It's because, as you saw, that's becoming very important for you. You read a lot of flat file, right? NGA is flat file, right? You read the VS30
from
okay, so
that flat file
can happen.
For the real observation, real ground motion observations. We had to come up. Where did this go? This thing is not cooperating. Let's try that. I was going to show you, but I got the wrong one loaded, so I'm going to go near the end and very quickly, I can tell because the hook is standing right there. This is for 0.3 seconds, the comparison we did before between larger magnitude and shorter. This is 0.3 seconds between including the intensity of data and not including the intensity of data. Not much different. PGV, where we don't have any observations from Bouge, makes a big difference whether we include it, and it actually lowers the ground motion estimates close in because you have some control as opposed to none, and so you're not projecting up without any return. At lower magnitudes where we have a lot of data, it has much less influence.
What is the vertical axis? Go back.
That is in G, the ground motion for peak ground velocity.
So I think we have to move on, but I think that what
basically, you know, if you don't really have any real observations, the intensity data may help provide some control.
Yes.
How good it is still has to be evaluated.
So this is a model in progress, and I think that we can work together with some of the products for the October workshop. So thank you for presenting a model that's in progress, because it's not easy. And then we can define maybe guides better to make sure that when we're at the October workshop and we have the real proponent discussions, that we have the plots that we need to see for that.
Is it possible to, if before October you have more information, you send it out?
Yeah.
Especially
it won't be before September. Naeem is going home to get married, so I have a complication.
Definitely, then you have to block that process.
Yeah. We're also, this summer, I have another student working on extending the different periods from Vancouver and Kramer to other 13 other periods, so we can get a better sampling in period, and that hopefully will be done before the end of the summer.
Just keep us posted so that we know what's going on, and we'll go from there. Thank you very much, Chris. So the next speaker is going to be Vladimir Grazier, and as we talked about it offline, this is also a skeleton model, so it's a principle. And again, just to get an idea, so we're not all blindsided with tons of new models in October. Okay, Vladimir.
Thank you. Okay, thank you, Christine. You gave a good introduction. This is I call it preliminary, but I also like the name skeleton model. It was designed in an assumption that I will hear a lot of information which will help me to constrain this model from this workshop. Okay, what is this model about? It is created based on April 2013. I will make it simple. Basically, the update that April did for NRC for nuclear sites, and it is based on again on April models, recent models, and cluster model, and on Chris Kramer database, which was provided by NJA to April. You can call it NJA East first version, whatever you like it, previous version of the database. Again, in contrast to Western type of attenuation, this clearly lack the data for near field and for large magnitudes. This is why kind of it put a lot of constraints, and it put a lot of pressure on the developer. Developer has to do something with near field and with large magnitudes. And again, as I mentioned, my kind of core model, core attenuation except the shape, except the form is based on April 2013 and specifically also SSHAC 2011 model. Like in a certain instrumental combination, I would call it this way. You will understand it. Okay, just to remind you, it was shown many times today. It is a database, distance, magnitude to distance. As you can see, there are only 3 data points with magnitude 675 from Nahani. Everything else is below 6, and it starts from 375. And in terms of shear wave velocity, it basically starts from 500 and end up at something like 2300 meters per second. And again, I didn't do anything with the database. I just grabbed it and used it. Okay. What is the basis of my model? My model is kind of based on previously published our model with Errol Kalkan. It's published in 2007, 2009, 2011. I use same modular filter-based approach. I know it gives heartburn to some people, but sorry, we use this term. And of course, since there are no data to justify certain things, I simplified in a way my Western model. Basically, there is no bump in this model, and it's not like I don't believe in bump. I simply have no confirmation that it exists in the data. This is why kind of I got rid of the bump. No Bayesian effect. I can implement it because I have a model from previous, but I didn't do it this way. No differences between fault style, again, because that's the typical approach. And it is all developed for average shear wave velocity of 1100 meters per second, which came from a simple reason. It's an average shear wave velocity from the database I got. It's nothing really magic in this number. Okay, I don't expect you to read this because it's kind of the model with coefficients, but basically I kept same form as it was before. It is 5 filters. Filter 1 is magnitude scaling. Filter 2 is core attenuation model. Number 3 is anelastic attenuation, side correction, and Bayesian effect, which again, in this case, Bayesian effect is 1. There is no Bayesian effect. But it is same style as it was before for Western US. Now, this is kind of, again, I know I was criticized for many years for this, but I believe this G2 is a shape of our PGA, and it looks like a typical single degree of freedom response, single degree of freedom oscillator. The good thing about this, it clearly has a flat area in the near field with a slope of R minus 1 in this specific case. Now, again, the beauty, I believe, of this approach is we have so-called corner distance, which is proportional to magnitude. Specifically, the larger is the magnitude, the longer, the bigger is this flat area. The smaller is the magnitude. You can see this with this, I believe they are red dots. I'm sorry, I'm partially colorblind. This is why kind of...
This is Norm, a quick question. To get rid of the bump, did you just increase the damping?
Yes, it's simply, in my approach, it's damping 0.7.
Okay.
Basically, no bump.
Vladimir?
Yes.
in order to go to magnitude 9, did you say you took advantage of position? How did you go to magnitude 9?
Okay, that's a stretch. I show magnitude, I didn't go to magnitude 9, but as was discussed before, for example, in Bob Young's presentation, we need to make sure that the model behave reasonably beyond the limits. The limits, of course, are about 8, but I just want to demonstrate how it behaves.
No, I mean
so in a way you can criticize me because I have saturation basically at about 8, not...
No, I meant even 8. How did you go to magnitude 8? Did you... I was...
Okay, I will answer this question in further discussion. It's a very good question, of course, very important question. This plot, please take a look at this. It's a demonstration of corner distance and behavior of my model. Basically, flat area up to about corner distance and slope of r-1 at some distances. And again, corner distance is proportional to the magnitude. Okay, this is magnitude scaling. I use same function as it was before, of course with different coefficients. It's arctangent function, which saturates at certain magnitude. And I will explain in details, in more details, how it was done later. But basically, in a way, it's coming from a combination of my scientific beliefs and Western U.S. Now, speaking about geometrical spreading, I tested EPRI models, and I found out that basically the final geometrical spreading that fits using my model is r-1 with anelastic attenuation. Anelastic attenuation, I used basically Q0. It is not varying, but it's Q0 coming from regional geology or whatever regional information. And again, speaking about reminding my model is has spectral shapes which are anchored at PGA. This cartoon at the low end shows basically same as it was in Western U.S. With a flat area near zero period and with certain bump, not bump, it's not a bump here, but it's typical shape of spectral acceleration. Now, it's a combination of two functions, same as in Western U.S., but with a different coefficients. Now, I will show a little bit more how those coefficients were found. Now, this is an example of spectral acceleration functions which comes out of my model. As you can see, again, I'm showing this from magnitude 4 till magnitude 9. I don't care about magnitude 4 at all. I just show them for kind of constraints. And same, I care about magnitude 9, but I cannot do anything about magnitude 9. This is why kind of, in a way, it's my whatever, scientific feelings or whatever. But it simply shows how the model behaves. Basically, just to make it plain and simple, my model is saturating at about magnitude 8. I don't have this oversaturation that SSHAC has. But in a way, it's certain numbers, it's similar. Okay, I go forward. Now, basically to answer the question that I have, I decided in this case, since of course, first I looked at the data, and I realized that data doesn't help me at all. I cannot do anything with the data like I did in the same way as I did for Western U.S. This is why kind of my basis were what Bob Youngs and others did in April 2013. I just took their clusters. I took their final model. It is shown here with yellow line with black dots, and I tried to fit my model to their model. This was the first step. I didn't think at all. My technical thinking was zero. I was just trying to match my model with different spectral shape to the model presented in April 2013, considering this to be a first step in my modeling. And at this plot, you can see, yes, another thing which Bob mentioned. All this model was done for 7 frequencies. 7 frequencies important for nuclear engineering. And I did same thing. I did 100 hertz, 25, 10 hertz, 5 hertz, 2.5, and 0.5, 1 and 0.5. And again, this plot shows my model, of course, adjusted after all using data, compared to April 2013 and to all clusters. Again, this is for magnitude 7.5 comparison. Yes?
This is Norm. Can you, I don't know if I missed it, how are you deriving the magnitude scaling?
Magnitude scaling is kind of driven by April 2013.
So is it right to say you've adopted the magnitude scaling out of the EPRI model and brought that into your second piece?
That's correct.
Okay.
That's correct.
But Vladimir,
yes,
you anchor your spectral shape to PGA, right? Yes. I miss how you're gonna link this to PGA. I can understand the way just Norm said. You take it out of EPRI and then you adjust it. But I thought that your spectral, how you're gonna use this for your spectral shape?
Okay. It all comes together. In a model, it's all come together. Basically, I looked at each frequency and compared it to April 2013, and this was the basis of scaling. Maybe I don't understand your question completely. If you
have different frequencies here, right?
Yes.
And then if you go back 2-3 slides for your spectral shape.
Yusuf, can I try to say what I think he's doing, and correct me, Vladimir, if I'm wrong.
Mm-hmm.
He's trying to find a functional form that is flat and goes to an attenuation. So it comes in flat at 0 distance and attenuates. To do that, you could adopt a lot of different forms. You could use we've used hyperbolic tangents and those types of things as well. He's adopted a form that is the form of a single degree of freedom oscillator with 70% damping. It's just the form of an equation for him. It sets the whole shape of the thing, and he moves what we would have had of a magnitude-dependent pseudo-depth, or how the saturation, he moves this corner with magnitude. Okay, that's all that's used. That's not defining the frequency content at all.
Yes, and it's a good point. That's what I realized, that I don't need this fictitious depth with this corner distance.
You capture geometrical spreading and pseudo depth with this one shape.
Correct.
Okay, so I think that's important for us to realize what he's doing. This just gives him something that sort of ties it together across magnitudes and so forth, without having the terms that we stick in there. But
right. It has, of course, as Norm just said, as you can see, it has some advantages and disadvantages, because in a way, I have to rerun my approximation many, many times, because I have to adjust both PGA and spectral shape, and each function has its own coefficients. It's like about a dozen coefficients. This is why kind of it's multi iterations process. And this shows comparison for magnitude 7.5, and next one is magnitude 5, also shown in EPRI. Again, somebody asked me, it's not completely, I'm not saying that I followed SSHAC, because as you can see, for example, at some frequencies it's much higher. But it's based on basically EPRI mostly and SSHAC. Now, next step is, of course, the most important, comparison of results with the database, which I had. And this plot shows how my attenuation compares to 100 hertz, 25 hertz data, 10 hertz, 5, and all these 7 frequencies. And of course, honestly, it compares well. But, yes, I'm showing residuals. Residuals are pretty good. But I don't make big deal out of this because this is all from magnitude basically 4.5. I got rid of whatever is below. It's shown in blue. It is okay. But again, please consider this to be an initial model. I was hoping to get some advice or constraint from this meeting. Now, standard error that I had, it's unbelievably low. It's like about 0.4, and it's independent of frequency. Again, I don't believe in this. It's an artifact of lack of data. This is why kind of in no way I consider this to be a standard error. That's what I was hoping to hear from this meeting. Basically, I would like, if I use this model, I need to implement certain epistemic uncertainty model, just basically put it here. One way is just to adopt something from Western, and in Western U.S., of course, it's going up with periods.
Just to be clear, are you talking about the aleatory term?
Yes.
Okay. So you said epistemic, but you meant the aleatory.
No. I'm saying in the future, I would like to add something.
So you would add epistemic uncertainty to the median, but the aleatory you're going to bring from somewhere else.
Correct. That's the plan. But again, it's kind of too good to be true, it looks like. Now, okay, I'm showing this plot not to criticize anybody, but just to bring to your attention that, again, I was hoping to hear this from this meeting. This comes from April 2013. And since I was a reviewer, I had to look in details in all this stuff. And what I found out, this is a correction from 760 to 2800. And 2 of these curves are Atkinson-Boor. Sorry, I have to put my glasses. It's Atkinson-Boor 2006, Atkinson-Boor 2011, Atkinson from the Canadian maps, and EPRI. And as you can see from this, these corrections are kind of contradicting each other from my point of view. What I was hoping to see here is something which will help me to deal with this issue, because basically my average airway velocity is about 1100, which I can drop to 760 and get. Anyway, I was hoping to hear what to do with side correction, especially at least from 760 to 2800. And so far I didn't hear anything, and the only thing I got looks to me controversial from every project. Now, formal kind of results. This model is designed for stable continental environment. Functional form works for magnitude 4 to 9. Actually tested, I would say, from 4.5 to 7.5. And again, larger magnitudes come from EPRI, not from my. And EPRI means it is Atkinson-Boor model, it is Toro model, it is Bezeshk model, it is Silva model, it is Somerville model in certain combination. Rupture distances, I put 0 to 1,000 kilometers. Period range, again, I tested this up to 10 seconds, but actually data test is up to 2 seconds, and it's extrapolation till 10 seconds. And it's for average shear wave velocity of 1,100 meters per second. Now, clearly, again, I was kind of expecting a little bit more probably from this workshop. I'm sorry. I was expecting to get magnitude scaling from kind of at least simulations, and at least I didn't see it. Again, I was hoping to get enhance of empirical data set by simulations for large magnitudes and close distances. Sorry, I didn't hear this. Site conditions also, again, didn't see it. Probably standard error is the thing that I can somehow implement based on this workshop. Thank you.
Vladimir, this second bullet, unless, God forbid, we are going to have a magnitude 7 or 8 in the East Coast, we are not going to have anything on the second bullet. We are not going to have any more data, large magnitude, short distance.
I realize this. This is why kind of my options is to stick with whatever I have, or find something else. I don't know.
The bullet says he wants to supplement with simulations. So
yes,
we can do that once we have them. We'll be happy to share them with you.
Yeah. No, I was talking about empirical.
Yeah, but enhance the data set with ground motion simulation.
Yes, that's.
Pay attention. Read the words. Okay. A little bit like we had for Chris. This is again a model in progress. So you have to keep us informed as it progresses and as it goes, so that we can be ready for to look at it formally in part of our assessment.
Part of what Vladimir's pointing out here is for him to improve his model, he needs more collaboration with what we're doing. So how we need to get a framework where as results come out, we can put them up so other people can be using them or implementing them, right? And not say and put them at the end of the project.
Exactly. Thank you, Norm. That's exactly my point. If I can be included in the group and share.
You have been. You replied to the doodle, right?
Thank you. Yeah,
we have started initiated for the next several months GMP working group meetings that will have weekly calls for all the model developers, to both those who want to develop models, but also for others to join in, and so we can have feedback as part of the development process. And people who want to develop their own model as part of that can do it as well. We're going to share the information, but this is also to serve as a feedback community for the models that are being developed. So, yes, you'll be informed.
Perfect, Christine. Basically, that was the purpose of presenting this model. Usually I don't present something which is kind of in this stage of development, but I wanted to bring to your attention that model, zero approximation model, if I would say, exists and works, and clearly desires certain improvements. Thank you.
Okay, thank you, Vladimir. So we're overdue for a short break. Since we want to keep some time for discussions, keep that at 10 minutes. So we'll start at 10:15. again with Ken's summary of hybrid empirical models. Okay, everyone, we're going to start again. So the first presenter, we have 2 presentations left. Gabe Toro, you better pay attention. I have to pick on different people. Okay, we have 2 talks coming in, and this first one by Ken Campbell is a summary of the hybrid empirical method as a whole. Is really how the method works mostly, and the description of that. And after that, we'll have a proponent model or approach for NG standard deviation.
Oh, now it is. Okay, thank you. Okay, so I'm going to just describe the hybrid empirical method, basically, and I'm going to show you a comparison of the existing hybrid empirical models that are out there, and then some conclusions. So anyway, the hybrid empirical method, or the HEM, or HEM, it was proposed by me first to be an alternative to the intensity. This goes way back, right, to the 80s and earlier. The intensity-based method, stochastic and numerical methods that are also used to develop GMPs and engineering estimates of ground motion, particularly in regions of sparse strong motion data, which tend to be also the low seismicity and stable continental regions as well. So it's applied by adjusting empirical GMPs from one region, which we call the host in this method, to use in another one, which we call the target. And the target is often located in a different tectonic environment, for example, like I mentioned, the stable continental regions. Although it has been applied to other regions where there's very little data that you wouldn't necessarily call a stable continental region. Switzerland, for example, is sort of in between, and it's also been applied in parts of Europe. So the adjustments are made using seismological models that take into account differences in the source, path, and generic site characteristics between the host and the target regions. So this is a history. I'm not going to go into this because there's no time. I just want to show you of the availability. I first did this back in 1981 in a very simplistic way of doing it for the DOE systematic evaluation program, and then sort of developed it from then. The ones in red here, just as I flash through these pages, those are all nuclear-related applications. So there's like 3 pages of these things. So anyway, I'm sure the presentation will be made available, so anybody that's interested can look at all this stuff. So the general methodology is to select and evaluate a host, spectral acceleration, empirical GMP for a predefined site condition, which we normally use firm rock condition because we want to avoid nonlinear soil effects. And then we need to select host and target FAS, 48 amplitude spectra, seismological models. We need it for both regions, so this complicates it a little bit. And you're very aware of what these models represent, so I won't need to go through that. And then we use the seismological model, stochastic simulation, and RVT, random vibration theory, to estimate then the host-to-target adjustments for the spectral acceleration values. And this can be done to basically account for all of characteristics, those 3 things, the earthquake source, path, and site, or it can be done just for part of it. And in fact, most of the recent applications of the HEM have been to do what are called VS kappa corrections. So it's just trying to account for differences in the crustal profile and kappa between 2 regions. The latest being actually it's being used at the Hanford project. It's being done as we speak. So then we apply these adjustment factors to the empirical host, spectral acceleration estimates, and estimate then the target spectral values. And then if you need an actual GMPE, you just take that synthetic data, basically, and generate a GMP from it. So the advantages, it relies on host GMPs that are well constrained by ground motion recordings. It incorporates empirically based near source ground motion scaling characteristics. I think all these models we're seeing basically are trying to incorporate that in the model, either using simulations or some other approach. It uses relative differences between, when I say simulated here, these are stochastically simulated spectral estimates. So that hopefully cancels out some of the modeling assumptions. Rather than using them in an absolute sense, we're using them in a relative sense between the two regions. So the potential, again, continuing, it provides an explicit method for estimating aleatory availability, epistemic uncertainty in the median, and epistemic uncertainty in the aleatory standard deviation, if you want to go that far. And that framework is in my 2003 paper, so I'm not going to go into that either. Now, the limitations. It requires consistent, reliable seismological data and models for both the host and target regions. And let me say right now, the WNA seismological model is old. So it's not going to be of the same quality or reliability that the new CENA models are going to be. So I just bring that up because this is an important assumption that one has to make in doing this. It relies on spectral ratios that are based on small magnitude earthquakes, right? Because that's all we really have in the east if we're applying it in the east. And basically the seismological models tend to be calibrated based on small magnitude data that's available. And it assumes similar near source spectral acceleration saturation characteristics in both the host and the target regions. We don't know, really, whether we get that same kind of saturation in the east right now, so it's basically an assumption, and it's an assumption that everybody has to make now when they're developing models. It retains the same limitations as the host GMPs, so basically a paucity of near-source data at large magnitudes. It's generally, in the past, has been limited to magnitude greater than 5 and distances less than 100 kilometers, right? Because empirically, in the West, this is where the data were. Now, I would say in NGA West 2, we've increased that, or I say increased, we expanded that now to include magnitudes greater than 3 and distances less than 300. So that limitation has been improved a lot with the NGA West 2 models and data. And then it's dependent on the assumed functional form that you use. And it also assumes similar response spectral shapes between the empirical and stochastic spectral estimates. And this actually turns out in Pegasus we discovered that's a real issue when you're really trying to take something from the west with a cap of about 0.04 seconds and take it to something like the east with 0.005. That the difference in the shapes between the empirical models and the stochastic models at high frequencies, and I'm talking like greater than 10 hertz, becomes a big issue, and I'm going to demonstrate that here. Anyway, as the footnote says here, just say okay. How do I click? I don't know how to use a Mac. Oh, I'll do what everybody else does, touch the touchpad, great. Okay. Anyway, this can be addressed and has been addressed in the last few projects using the inverse RVT method that Linda Alatik particularly has been looking at. Or the alternative would be to actually develop models in terms of Fourier spectra to begin with. And so actually Bora et al. Has sort of demonstrated that in a European project, which is quite impressive. So I think that's probably in the future. So now I'll just show you some examples here, and I can go through these because most of this stuff has already been covered in the workshop. So I don't have, but here's the difference. On the left, you have the NGA West 1 database, and on the right, you have the NGA West 2 database. So certainly you can see how it was filled in at small magnitudes. So we now have good small magnitude scaling, which really will be important when we're trying to take these models and transfer them to another area. We still have the issue, if you look at maybe 7.2 or so, or even above 7, 7.2, it's still sparse. There's only a few earthquakes that are still controlling the magnitude scaling, and so that's still an issue even with the NGA West 2 data. I mean, just because there's no data. I mean, worldwide we've collected this data in NGA West 2. And then if you just look out to 80, though, from 3 to 8, you can see actually that within the distances that are really important, again, we have these gaps. It's interesting. We also have a gap between 5 and about 6. It's because we really didn't spend a lot of time trying to collect data in that area. And so I think to really get the magnitude scaling correct, we need to fill in there as well as try to fill in above magnitude 7. Okay, so this is interesting. This came out of the Pegasus refinement project. So on the top are a bunch of correction factors, we'll call the VS kappa correction factors, right, to take data from the west to Swiss-like properties. And so if you just strictly use the HEM, okay, the HEM approach above, this is the kind of correction factors you need to do. Well, some of these came out really high. So some of the models, the black, I don't know if you can see the black curves. The black curves are actually a 5-point fit to the distribution of all of these, right? So the middle black curve, yeah, you can sort of see them. Let me see if I can point it out. So right here, the middle black curve is right here. So see it, no it isn't. It's 1, 2, it's right here. Yeah, so there's the middle black curve. That'd be the median, right? And so that's using the HEM. And if you go down here and just say use the inverse RVT method, the middle black curve is this one right here. And not only does it peaks at 20 hertz rather than 30 hertz, but if you can see, some of these correction factors are really huge here as opposed to here. And Frank Scherbaum pointed this out to me. In fact, I think at the first NGA East workshop, and I sort of argued with him, but it turns out when I went back and looked at it, he was right. And I'll show you why that's the case. Okay, so here we go. Here's some adjustment factors from my 2003 model. It's a function of kappa and stress drop. Okay, so the median sort of that model was a kappa 0.006, stress drop of 150 kilometers. These are kind of correction factors in terms of PGA and SA that one would get. And so if you look at the high frequencies, so right here, this is 20 hertz. So that correction factor would be 3.5. Okay, now if you go to a smaller kappa, and for the median delta sigma, here now you're getting a 7.7 factor of 0.0. These are significant factors. And so if you don't have the high frequency part of the empirical model, if that isn't fitting the stochastic model that you're basing these factors on, then you're going to overestimate the effect. And that's in that previous slide I showed you, that's what was happening. The good news is Linda figured out how to correct for that. So, but I just want to point this out because this is an issue with the traditional way of doing it. You can see also, I think, that the effect of stress drop is really less than the effect of kappa. So kappa really becomes the important factor to try to take into account here, particularly when you're going to these really small kappa areas. Here's the problem. Okay, this happens to be from my 2003 model, so these are based on the older equations. And NGA West 2 I haven't looked at. They're certainly pumped up in the high frequency region, so they may not be as bad comparing it to stochastic models, but this is really showing the issue. So you can see the empirical model, see what they're doing here? They come down and they just come out at a higher region than the stochastic model. So, you know, right in here, they seem to be fit quite nicely. They're not fitting very well here. And that's those frequencies where those big amplifications are. And now you'll see these are spectra from the 2003, my 2003 hybrid empirical model. And see this kind of this bump in here, and then it kind of has a sag, and then it does this. This bump, if you did this with IRVT, this bump would come down, and you get something that actually maybe looks more like a spectral shape that you'd expect to see. Now, if you go to the other frequencies, I think they're pretty good because the spectra match pretty good. We don't have that bias. It's just in this really high frequency range, which is important for hard rock in the east. Here's an application that was done by Van Hout et al. And so this is kind of the VS30 kappa correction factors. So this is one application where the HEM was used. This is another application by Catona et al. I think this is for Pegasus. I think this one was for SHARE. SHARE was a European PSHA project. And this one, this is up here is just the VS30 adjustment, taking it to I guess in this case, the Swiss conditions would be that. And then here's when kappa was factored in down here. So these are just examples. This is another example showing you the importance of kappa. So now, can't see the thing, but if you look at, here's 10 hertz, here's 20 hertz is right here. So if we look at 20 hertz again, and you go from a kappa 0.04, which is typical for a soft rock site in the western U.S., and you're trying to take it, to a kappa of 0.005 or something like that. This is in Fourier spectral domain, but that's the kind of factors you're getting. They're huge, right? So it's really important to get this part right. This is the impact of kappa. This is from Walt Silva. This is the impact of kappa on the shape of the spectral acceleration curves. And again, you can see the very strong effect of kappa and how that shifts this peak as you go to really small kappas, shifts it to very high frequencies. Again, this is 10 to the minus, so here's 20 hertz. No, this is frequency, yeah. I have to be careful. This is showing, this is from my 2009 paper where I sort of looked at kappa as a function of sediment thickness. Martin showed a similar plot that he got for the Gulf. This is mainly driven by Atlantic coastal plain data, primarily Charleston as well as New Madrid region. But you can see there's a very strong impact of sediment thickness on kappa. So this is more in the side effect area, but it's very important. The pole sediments are the red, and then if we just chopped everything off that I used, chopped off the top part and only looked at BC, down to a BC, Nehert BC site condition, you would get the blue curves. This has been already shown. I just wanted to show the impact of the assumption of geometric attenuation. So this happens to be a different earthquake than the one that Dave showed or Gail showed. I can't remember who showed this one, but this happens to be the Rivière-du-Loup earthquake. But again, you can see that since it's anchored out here with all of this data, once you get into this region, you get some pretty strong differences depending on that. And that leads to, like Gail mentioned, really differences in the stress drop that you would have to also get from that, anywhere from, in this case, 70 to 340, similar to the range that Gail showed for another earthquake. Okay, so let me just show you a comparison of sort of the hybrid empirical models that are out there. I'm also throwing in Gail's referenced empirical approach as well, since it's related, but it's data-driven as opposed to using stochastic models to do those adjustments. It's the data itself that are used to make the adjustments. So it's a different approach, but similar in concept. So I like to include it in the comparison. And I'm not going to go through this. I just sort of trying to summarize the basic information that went into each of these models. I won't belabor this because I don't have time. But anyway, so Campbell 2003 model. You can just quickly look at this as I flash through them. The Tavacola and Possess 2005 model. And then I did, wasn't published in a journal. It was a NEHRP project and published in a NEHRP report and then in several other papers So that's why it spans 2007 to 2011. It's not a GMP per se. It's a tabulated, it's a tabulated GMP, or as opposed to fitting a functional form, because I didn't take the time to do that. And then the Posseshed et al. Application using, in this case, the NGA West 1 models, and then the Atkinson reference empirical approach. Okay, so here's a comparison. On the left is PGA. On the right is 20 hertz, or 0.05 seconds, and it's magnitude 5 and magnitude 7. And it's interesting, at least at the high frequencies here, there isn't a whole lot of difference in all of these models. They tend to coalesce pretty well, actually. And as we go to now 0.2 seconds on the left, 0.5 seconds on the right, now we're starting to see, at this period, we're starting to see some separation in the models. The referenced empirical model is rolling over, right? That's the flat part that Dave, what's your name? Yeah, Bob. That Bob shows. I only see him like every week, and I can't remember his name. So that's the flat part. You can see it really rolls over, and that's because it's based on the Bohr Atkinson 08 model, which has that same functional form. So it starts to separate out. You also see differences now. The blue and the green that's right in here, blue and the green that's right here are the two older HEM models, Campbell 03 and TP 05, compared to the newer ones, the Posseshed et al. And the CO7. And so we're starting to see those things separate out. And then when we get to longer periods, we even start to see that separation at the small magnitudes as well. Now, I'm going to bring up something. Bob mentioned in the EPRI model that they looked at the difference between R to the minus 1.3 and R to the minus 1 geometric attenuation. This separation is somewhat due to that because of the two older models are basically using R to the minus 1 in the west and R to the minus 1 in the east, whereas the two newer models are using R to the minus 1 in the west, but R to the minus 1.3 in the east. And the issue is, since the west really hasn't been looked at as carefully, should that be steeper or not? If you make that steeper, then I think you're going to see a very different type of scaling here. So I think this is the geometric attenuation in the out to 70 kilometers is one of the really important parameters, and as is kappa. Here's some sigma models. Some are flat as a function of magnitude. Some have magnitude scaling in at different levels. And then basically as you go to longer periods, they creep up. Okay, so general conclusions.
Chen, did you have magnitude scaling comparison?
No, I didn't. Yeah, of course. The reviewer of the paper didn't ask me to do that, and I didn't have time to do it. So.
No, I'm asking.
Too late. It's been published. Okay, so just to review, it's sensitive to the following factors: the form and scaling characteristics of the host GMP, the empirical host GMPs, the source characterization, stress drop being one of the more important parameters for that. The path characterization, both the geometric and elastic attenuation, but particularly the geometric, because that's what really impacts the close-in sites. The anelastic is really well controlled by data, so that's not as big an issue, but it is important. Site characterization, in other words, the velocity profile, the depth of the sediments, the site attenuation or kappa that you use in the east and the west, and the difference in shapes of the host empirical and stochastically simulated response vector. So I hope I basically made those points to you with showing you some quick plots on those. You need a reliable set of host and target seismological models. and they depend on the following factors: reliable sets of seismological data. We do have that in the West and the East, so that's not a big issue. Consistent set of assumptions, and so this is a big issue. For example, is R to the -1 really correct in the West, and R to the -1.3 in the East? That's a basic assumption that was made in Pizzesk et al. On CO7, for example. And we don't know. I think Gail's been continuing to do a lot of work, as well as others in the East, that same level of effort isn't being done in the West because we haven't good empirical models. But in order to apply this HEM approach, you really need the Western model to be as good and up to date as the Eastern model. We need to maintain correlation among the parameters. This has been covered. You can't just take stress drop here and geometric tenuation there and all that kind of stuff. You have to have a coherent model. Okay, and then applications of the HEM have shown that it is a viable alternative to stochastic and numerical methods, and is typically used in the national hazard maps and the EPRI study and other studies. So I don't think I need to convince anybody. But here's the practical conclusions after all of this, and Christine's going to wish she hadn't invited me now. But the NGA's project will develop reliable, updated seismological models, right? But only for the East, not for the West. So now this gap is even growing. We're even going to have a better set of Eastern models and still the same old 1990s models in the West. And so until there's time, and there's certainly no time to go and try to develop good models for the West at this point, because nobody cares, so it would have to be done by me if I need to do that. That's not going to be done. And then really now, since the schedule's gotten compressed, by the time the seismological models come out, there's only a few months left between when the GMPs have to be delivered. So that's impractical as well. So basically, I'm going to have to say that there's not going to be a HEM model developed by me for purposes of the NGA East project at that point.
NGA East 2.
NGA, yes. So I still want to do it, but it's going to have to be done after the project, and it's probably going to take about a year to do. So anyway, however, that doesn't mean that the older HEM model shouldn't be considered in the evaluation by the TI team. I think they are still valid, and particularly if you account for these particular issues and take those into account. There's still a lot of good information in there right now that should be factored into the evaluation. So for future, so now I'm talking, past the due date for the NGA East models. I think the NGA East results, once they're finalized, can be used. The NGA West 2 GMPs can be used for the host models because they're much better, as I showed, and I think will improve the HEM approach very nicely. And then may even consider finite fault as opposed to point source stochastic simulation to do the adjustment factors. Of course, all of this depends on having an updated and consistent host seismological model for the West. And then in the short term, explore the use of RVT, so convert the host SA estimates to FAS using IRVT, apply all these adjustments in the frequency domain. And that's what that's the way the TI is going to handle it, and then convert it back into the spectral domain. So this is similar to their approach, except they're going to look at FAS directly. In the short term, since we don't have FAS models in the West, then I would propose we can sort of approximate them with IRVT and see how that works. And then finally, I think, and I'm going to say NGA West 3 with a question mark, one of the proposals is that we
No question mark.
Oh, okay, good. We will then look at Fourier amplitude spectra GMPs for NGA West 3, and then use the approach that Norm has been proposing have a consistent duration models to go with those. And I think that would help a lot. That would eliminate some of the issues that I brought up with the HEM approach by having a good set of spectral, Fourier amplitude spectral models for the West. And then we would go through that same process I just mentioned, except we would do it with actual Fourier amplitude spectral models rather than converting it to I or VT. And I got lots of references. So those are references by me that are listed in that big table primarily, and then other 3 pages or 4 pages of others. So, thank you.
Thank you. Gail?
Gail here. Just make a comment. It's not quite as grim as all that. There have been, I've got a couple of PhD students who have been working on modeling equivalent point source models in both the West and the East over the last couple of years. And one of them, Emra Yenye, there's one paper that's in press on modeling some of the larger events, and then there's another one that's in preparation that will be ready in another week or so on developing those models, attenuation and source for the West that can then be used in the hybrid empirical. And another student, Bizad Hassani, who's been looking at those referenced empirical corrections for the East and how they compare with the hybrid empirical approach in the East. Great. And that one's also in preparation and will be ready in within the next week or so. So actually there has been quite a lot of background work on model development in both the West and the East that we can make use of in this project to the extent possible. Whether it still matches your time frame is is another question. But there has been a lot of work on those specific questions. Good. And I guess just in particular the one that you mentioned, the geometric spreading. Right. I think the answer is yes, it's steeper than r to the -1 in both the West and the East. Okay. It's the small magnitude data basically that constrain that. You can't tell in the West at large magnitudes because of the trade-off between the saturation term and the geometric spreading, which basically masks the geometric spreading. But when you look over the wider range of magnitudes, essentially r to the -1.3, both East and West.
Wow, okay, very good. Well, so it looks like we will have that information available, but yet the timing is still an issue. So thank you, Gail, and that gives me encouragement that over the course of the next year, it would be, we'll be able to do that. Pardon? Yeah, keep me informed. I would really appreciate that. So, okay, thank you.
One question, can I?
Oh, yeah.
Okay, well, I hope it's quick. One could argue that the total epistemic uncertainty you get when you apply the hybrid empirical is going to be the combination or the SRSS of the epistemic uncertainty in the host GMPE plus the epistemic uncertainty in the host stochastic plus the epistemic uncertainty in the target stochastic. To what extent is that true, and to what extent that is a problem?
Yeah, in 2003, actually, I did all those calculations, and yes, certainly the epistemic uncertainty in the host is important to consider. The seismological model, because basically you can, hopefully it fits the empirical data, or if not, maybe you adjust it. But anyway, you should be able to get a pretty good fit to that. So in the past, that's been ignored because it gets swamped basically by the uncertainty in the eastern seismological model. So the western one is much better constrained because you can calibrate it to the empirical groundwater. Now that was a little bit of an issue because we didn't have the small magnitude data. I think it's even better now that we will be able to compare it and possibly calibrate it to the empirical data, having magnitudes 3, a good database from 3 up to 5.
Okay, so Gabe is the microphone keeper. Thank you, Ken, very much. And yes, next and last talk of this 3-day galore of presentations is Linda Alatic talking about the NGE's approach for modeling the standard deviation.
Good morning. All right, so I will today describe the objectives of what is the TI team's plan in modeling the standard deviations of the ground motions and its different components. I'll give a brief overview of residual components and the aleatory variability. Also an overview of the available data and how we can use it to move forward. And in parallel to that, what are existing data and models that we can also learn from, and a few other things that we can think about as issues to be addressed. Okay, so this goes here. All right, so the objective of the project is to develop models for the between event standard deviation tau, models for the ergodic within event standard deviation phi, and models for the single station within event standard deviation phi SS. And these need to be applicable from magnitude 4 to 8.2, distance up to 1,000 kilometers, and hard rock sites. Okay, so this is the PDF, right? All right. All my fancy animations are gone, but that's okay. So here is a description of the residual components, and I don't need to spend too much time because Christine has put that up for reference on the web. So if delta is the total residual, the misfit between the observed ground motion and the median prediction from the model for an earthquake E at a station S, this can be divided into two components, the between event residual, delta BE, also known as event term or inter-event residual, and the within event residual, delta WES. So if we look at this plot, the between event residual is the average deviation of the ground motion recorded for a particular earthquake from the median ground motion model. The delta WES becomes the misfit between the ground motion recorded from this particular earthquake at a certain site with respect to the earthquake-specific median prediction. The standard deviations are tau for the between event residuals and phi for the within event residuals, and combined they give us the total sigma. So we can even go further into dividing the residuals. If we have multiple recordings of ground motion at an individual site, we can estimate the systematic site effects. We call those delta S to S at the different stations, and we can remove that from the ground motion variability. By doing this, we can get the single station within event standard deviation, single station phi. So what delta S to S is then, it's the systematic deviation of the observed amplification at a particular site from the median amplification predicted by the model. So in a simple way, we can, in a simple way then, delta S to S would be the average within event residuals at a particular station. We can take that average out from the within event residuals. We can get the single station within event residuals. Their standard deviation would be the single station phi. The standard deviation of the site-to-site term would be phi S to S, and that goes to the epistemic uncertainty. So then phi can be divided into phi SS and phi S to S. In summary, we have here the ergodic components, and here the partially non-ergodic, and so we have delta WES within event residuals. It becomes single station within event residual after taking out the site term. Phi goes to phi SS, and sigma to sigma SS. So to apply using the single station approach leads to a reduction in the aleatory variability. However, that requires in forward applications to quantify the site-to-site terms, and that can be done by using recordings at the sites or site response analysis. The epistemic uncertainty on the site term needs to be accounted for in forward applications, and we also need to account for the epistemic uncertainty on PSS, and that would be part of the modeling that we will do here. So this is, we saw this a lot of times. So this is the data set for NGA East, magnitude distance distribution, 82 earthquakes, 1,284 stations. So it's a lot of well-recorded earthquakes. On the right, you can see the histogram of earthquakes versus number of recordings been. And so we only have 5 earthquakes with less than 3 recordings. So we have a lot of well-recorded earthquakes. So to have a reliable event term, we need to take out the earthquakes that were not well recorded. So if we take out these 5, then this is the magnitude distribution, distance distribution. But then looking at the frequency of stations that recorded different number of recordings per station, a lot of stations have less than 3 recordings each. So we cannot really use them to have a reliable site term estimate. So if we look at the part of the data set with a minimum of 3 recordings per earthquake and 3 recordings per station, this is what we end up with. We have about 9,000 recordings, 76 earthquakes, and 905 stations. Maximum magnitude is 5.8. And we don't have anything beyond that. So how do we go forward? So for the plan is to use the NGA East data set and analyze residuals within event residuals and between event residuals with respect to developed GMPEs that will have, evaluate any dependence of phi and tau on magnitude and distance dependence of phi, and then compare these results to results from other data sets where we have overlapping magnitude distances, and then hopefully learn how to go forward and extrapolate. Similarly, for PSS, we will analyze the data that we have, look at trends, magnitude distance dependence, main shock, aftershock, and then compare these results to what we have from other regions, particularly the NGA West 2 data that encompasses the large magnitude distance range, and see if we can adopt something. So I will just give a brief description of what is available, what we can look to use. So this by no means is this list exhaustive. So I just put a few of the recent studies with somewhat large data sets from different regions. So we have the Rodriguez-Marek et al. 2013 data set that was collected for the Pegasus Refinement Project. It has data from California, Taiwan, Switzerland, Japan, Turkey. We have the NGA West 2 data. We have the Lin et al. Data from Taiwan. Atkinson 2013, small data set from Canada, but this is relevant for the NGA East and the conclusions that she found there. We have European data, and we have Japanese data that's being analyzed. So I will only talk about the active and stable regions. Let's look at the data that was collected for the Pegasus Refinement Project. So on the left is what they had. They had magnitudes 2 to 8, up to about 200 kilometers. This is what we have in the NGA East data set in comparable magnitude distance ranges. So basically, we have some overlap with them that we could compare their results with what we have in this magnitude distance range.
Linda, in
in
the previous figure, the left includes active regions also? The data in the left?
Left, yes.
It has to.
Yes. They found, one of the things I'll say, that there wasn't regional dependence of VSS, so they could use everything together. So the models that they have are applicable for a magnitude greater than 4.5, distance less than 200 kilometers. They have proposed models of VSS that are constant, magnitude dependent, distance dependent, and both magnitude and distance dependent. This is an example of their results. On the bottom, this is the phi, ergodic phi, split by the regions that they had the data from. And on the top is VSS. And one big thing they observed is the lack of regional dependence of VSS here. As part of the SWOS/peer effort, we looked at the NGA West 2 data. We analyzed that for a single station phi. And we added to that additional data from Taiwan, from Lin et al. So basically, I looked at the residuals of the 4 NGA West 2 models that had, so IDRIS didn't have the division of the residuals, so it's not in there. All 4 NGA West 2 models showed consistent results. So I'm just going to show a few things from the analysis of this data set. This is data distribution. I think this is based on the ASC14 model. So in red, you see the Taiwanese data, but this is not just what Norm had. This is supplemented by the Taiwanese data from Lin et al. So you see also lots of data from Taiwan. This is now a comparison of the West data plus Taiwan to the East. And we have some overlap between magnitude 3 to 5.8, distances up to 800 kilometers. And where this overlap is mostly California and Taiwanese data. This is a comparison of phi and VSS for the ASC model. This is all his data sets. So in red is phi, and then you see in blue the reduction that you get when you look at the single station phi. This is just to show the results of the analysis of all 4 NGA West 2 residuals. So here is VSS using all the data, all magnitudes, and you can see that they all agree very well. And this is here using a subset of magnitude larger than 5, and they still agree pretty well. Regional dependence. So this plot is a little bit busy, but basically what you see here is the analysis of the ASC14 residuals plus the additional Taiwanese data. So the data points in black, this is the entire data set. Now in blue is California only. In pink is Japan. It's not a lot of, basically I think 3 or 4 events. In red here is Taiwan, as it is in the ASC14 data set. The red triangle is Taiwan plus Lin et al., and it was only available at 5 periods, so you don't see lots of points from it. And the green is the Italian, the results from the Italian data, which is not that much, not that big of a subset. So if you look at this, you can see that there is not really, so there is a regional dependence. And that was kind of contradictory to what the PRP study has found. But then again, we went back and took out all the small magnitude data. So if we look at magnitude 5 and larger, you see now that California went down. So this is California in blue. Now it came down, and it's consistent with the Taiwanese data. We cannot really say much about the Japanese and the Italian because there is not much data there anyway. So I still think that maybe we can find some regional independence of VSS, but we need to see how it looks for the NGA East data. Yes. Well, at least based on this, for larger magnitude, you are saying for larger magnitude.
Then, Linda, I was curious if for small magnitude you could compare with what Adrian has collected from Japan.
Yes, I have a couple of slides on that.
Right.
So I don't have results because he sent me some plots last night, but I can say something about it. Magnitude dependence of VSS. So this is looking at the NGA West 2 data. You see some clear magnitude dependence. VSS is much larger for magnitude 3s and 4s and goes down with magnitude up to 6. At longer periods, there isn't that much of a magnitude dependence anymore. Distance dependence, and here these plots show PGA on the left and 1 second on the right. The black points are all magnitudes lumped together.
Can you go back to the previous slide?
Yes.
Any explanation for why VSS goes up above magnitude 6?
No, I don't have an explanation, but basically the way we modeled it for SWOS is constant.
Okay. Because it's very strong decrease, a very strong decrease up down to 6, but then it goes up again.
Yeah.
Okay.
So for distance dependence here, we can clearly see a strong distance dependence when we look at all magnitudes together, but that is mainly an artifact of the small magnitude again, because when you look at data with magnitude 5 and larger or 6 and larger, you don't see that magnitude dependence anymore. Oh, this is just from another. Global is basically NGA West 2 plus Taiwan, because sometimes I look at California only. All right, so I also looked at VSS using European data from Akar et al. For the SWOS project. So this is their magnitude distance distribution. They go down to magnitude 4, distances up to 200 kilometers. And this is a comparison of the VSS that I got from the European data in blue compared to the ASC14 VSS. It's generally comparable at short periods. At long periods, it just has a different something else going on. I also saw no magnitude dependence, pretty much, of VSS using this data set. But then again, they only have 3 earthquakes with magnitude greater than 7. So. Adrian Rodriguez-Marek is analyzing data from Japan, from the KickNet array. He processed, I think, 100,000 recordings and developed GMPs, and he just sent me some preliminary results. So his data set is magnitude larger than 4. He has both surface and borehole recordings. This plot here shows the VSS that he gets. And we're looking here at the lines. This is his recent result compared to VSS from the Pegasus refinement project. And one thing he said that he observes generally slightly larger VSS for Japan than what he had seen before. And one interesting observation is he did not see any magnitude dependence of VSS for Japan.
Is this combination of subduction and crossover?
So I think they divided them, but I don't know exactly what this VSS is. He did split the data, but I don't know what he sent me exactly, so it's a little bit premature. This is the VSS analysis that Gail did for 6 stations in Canada. So this is the magnitude distance distribution, and she compares them to VSS. So she compares the VSS values to VSS she got in California for 2006, and the interesting thing is that they were similar. Okay, other things that we need to consider is the epistemic uncertainty of VSS. So we can do that by looking at, so there is this epistemic uncertainty on VSS comes from azimuthal dependence, topographic effects, and other unknown factors. And to get an idea of this epistemic uncertainty, we can look at the station-to-station variability of VSS. So now we have an additional S, it's VSSS, which means it's VSS at a particular station, and then apply the station-to-station variability as an epistemic uncertainty in VSS. To do that reliably, we need to look at stations with a lot of recordings. And as the number of recordings increase, the standard deviation becomes smaller. So this is something that Adrian has done on, I think, on Pegasus or maybe other projects, and that we did also for the SWOS project. So to estimate the sampling error and its effect on the standard deviation of VSS at the stations, we can do the statistical exercise of simulating a lot of recordings per station, for example 3,000, and assigning to them a particular coefficient of variations. And so we can then take out smaller subsets of n and compute the coefficient of variation from these smaller subsets. So if you look here in this plot, this solid line shows this exercise when we assign that all the stations have the same standard deviation, have the same VSSS, so there is no standard deviation in VSS. You still see that when you sample 10 recordings or 20 or 30 or even 50, you see a coefficient of variation. And so this shows purely the sampling error. These points here show the standard deviation of VSSS from the data set of NGA West 2. And basically we use this exercise to say that, okay, we can use a coefficient of variation of about 0.12 to tell us really what the standard deviation of VSS is. So we're trying to take out an estimate of the sampling error. Additional considerations, I guess for this project, could be for NGA East too, I don't know. So the within-event residuals have been observed to be spatially correlated. Jack Baker and his students have done a lot of work on that. They found that this spatial correlation has negligible effects on the GMPE predictions, but it impacts the estimates of tau and phi. The way it works is that it causes a decrease in tau and an increase in phi. So this is an example of the work that SSHAC did for the SWOS project. He analyzed the CY14 data set, and here he's plotting the ratio of including the spatial correlation versus excluding it for both tau and phi and also sigma. So tau 1 is the values that he gets for magnitude less than 5, tau 2 is for magnitude greater than 7.25, and the green line is basically lumping all the magnitude together. So as you see here, there is a decrease in tau, an increase in phi, and an overall maybe slightly increase in sigma. So we looked at this for the SWOS project using, so this is just using the within-event residuals, not the single station ones. So I looked at it for the single station, and there is a spatial correlation again. We haven't yet quantified exactly its effect on VSS, but this is something that we may consider for this project. Other things that have come up recently is the tail distribution of ground motion residuals. So there has been an observed deviation from the log normal distribution that we've always assumed in the upper tail of residuals for both phi and VSS, and Bob Youngs has worked on that for the SWOS project. And you can see here on the left is the QQ plot for log normal distribution, and you'll see that the upper tail deviates. And then if we model this as a mixture of two log normal distributions with different sigma ratios and different weights, then we can capture this tail pretty well. Okay, so this is my last slide. So in summary, VSS may be region independent. particularly in specific magnitude distance bins. I put a question mark because we will see. We need to compare and see. So also there is an increase in PSS at small magnitude and short distance, and other considerations that we need to discuss here could be part of this project or not, but I just put them. Yeah, that's it.
One question, Linda.
Yes.
Actually, can you go back to one of the tails?
Yeah.
Remind me, are the tails fatter than normal or thinner than normal?
Fatter.
Fatter, okay. So it is
yeah.
a potential concern, especially in the PRA world, for example.
Mm-hmm.
That's looking at 10 to the minus 6 and lower probability.
So the tests that we've done so far, both here, so we've looked at this at Hanford, and we've looked at it, and we are looking at it for SWUS. And the issue of the heavy tail or mixture model starts to appear if you're getting hazard contributions from epsilons above 3 or so. So that's where it's starting to appear. So if you're typically in the 1 to 3 range of epsilon, then it doesn't really matter that much. But once you get out beyond about 3, it shows up as showing some significant difference, quote, significant difference in hazard.
And it's probably more important in the east than in the west, given that we have lower rates. Oh, no, it's not the rate. The M max may matter. Yeah. Okay, because of the M max. Okay.
So it becomes, I think, more important when you are basically getting, for instance, it'll be important from contribution from New Madrid, because there the rate is high, and so at low probabilities of exceedance, you're basically getting the sampling out on the epsilon tail, on the ground motion tail. The event's not getting any closer. It's not getting any more frequently. It's just basically ground motion uncertainty. So at low probability, so that's basically where we see it. For instance, in Hanford, we see it more from subduction than from the local crustal events. Local crustals are epsilons of 1 to 3. Subduction is reaching 3 because it's 500-year return period, and we're at the tail of the ground motion. So that's where that's so far where we're seeing the effect.
Christine? Pay attention, please.
Thank you, Justin.
Ken Campbell. So Linda, I noticed in those recent results you were showing, you were using 3 records per earthquake and 3 stations per earthquake. 3 records per station. This seems to be a lot less than what, in fact, at one point in past projects, it was 10 was sort of the minimum desired, and then to get records down to 5, now you're going down to 3.
Yeah.
Is that causing a creep in the PSS that you're estimating? And
yeah, so
maybe you shouldn't go to such a small number of earthquakes and recordings.
So I am not just averaging the residuals. I am using the mixed effect algorithm, which allows me to get somewhat reliable estimates with a small number of recordings. And I did also compare using 3, 5, 10, and it wasn't a big difference for NGOS2 data. It was very comparable. So I decided to maximize the data set.
Ken, it's a bigger issue when you try to do like the individual PSSs at a site, then you really can't get them. But the magic of the random effects is you can get a site term from a single recording, and it's going to partition the variance, right? You could do it for different subsets. And so I think already going down to 3 is probably fine in terms of what we're trying to do. So it's going to look at the variance of the well-recorded sites, right, that have lots of them, and assume that those sites with just 3 recordings are samples from that same variance, and then figure out sort of what is the estimate of what the mean value would be. But probably the thing here is to run it with a few different cutoffs and see if it's changing.
Yes, I've done that, and I will definitely do that again.
Okay, so one thing here that's very important for this project, even more than others, is using this PSS approach by taking the delta S2S allows us to deal with the true observed repeatable side effects. So that's better than just only relying, obviously, on the VS30 scaling. So that's a really that's a good thing for us. Where we're not sure what's happening, we can at least see those side effects out, even for misclassified sites.
I have a question that relates to that, and maybe it's a little bit broader than and it may need comments from Linda and others. And it's that when you use PSS, you have to make sure that the side effects are captured properly. Will this project go into any detail as far as giving recommendations for the site response analysis? Is that part of the scope, or how is there a process to make sure that site-to-site variability is not lost, especially at sites, like most sites in the East where you don't have any local recordings?
Do you want to answer that, Youssef? It's not part of our scope.
We are going to provide fee for people who are not going.
You are going to provide.
Yes.
Okay. Yes. Okay. Ergodic fee. All right. Okay. That takes care of the issue. Okay.
We are not adding scope any way here.
The other question now that I have the microphone is the question I had asked yesterday.
Can you take the microphone?
The question I had yesterday, does anything about Saguenay and mineral makes us rethink the idea that P or PSS or sigma are the same in the East and elsewhere? And one good thing is I saw you're talking about doing some of these analyses in the East and looking at overlapping data sets and so on. The one concern I have is that the 2 events that seem to show anomalous things are the largest we have that are truly Eastern events.
Yeah, I cannot answer this question. It's something that we need to look at. When
What did you just say, though? The 2 events that we have are what?
Largest.
The largest values of the standard deviation.
That have large standard deviation. And the large magnitude, large standard deviation. What I was going to mention, though, is I think it's partly a data quality issue for those events in that for Saguenay, it's the stations in Charlevoix for the Saguenay earthquake that appeared to have those large side effects and large phi. Those were strong motion stations in Charlevoix. But the study that I did that Linda mentioned, the 2013 study looking at standard deviation, was in fact in the Charlevoix region for the permanent network stations in Charlevoix. And the phi values there are really very low. So I don't think that it's a generic problem that phi is greater in the East. I think that there's some particular data issues there.
So this is something the the Sigma working group is going to look into, and first, again, looking at the overlapping data, and then see differences in the few data points where we have phi. That's part of their mandate to really look at that. Okay. So, another question for Linda. So that's the CI team plan. So I guess we're going to be ready to just show the summary of today's presentations, and we can wrap up. You good with that? Norm is still typing. Oh, he's checking.
take that and so fat tail distribution, I think, is we include it and we just move on, right? The data that we have that suggests fat tails, we don't have anything suggesting not fat tails. So I think that's the easier model to take, and as opposed to trying to start over on that topic. It's really fat above 3 standard epsilons of 3, so whether that has a significant impact or not, we'll have to see, but it wouldn't be until really far out. When you've run, are you ever getting contributions above 3 epsilons on any of these eastern sites?
You need the mic.
The code I use in the east doesn't give me epsilon, so I can't say for sure, but I would guess we're getting some contributions, especially at low frequencies from New Madrid, where New Madrid is the dominant source, even to 10 to the minus 5 or 6. We're probably getting to 3 epsilons, I would guess, at low frequencies from New Madrid.
Christine says yes.
I mean, regarding the fat tail, it's not something we have really the time to look into, and we don't have all the information to do that right. I think that's the best is just to adopt it.
Also, that's a good topic for the workshop 3 sensitivities that we
see that if it matters.
plan to see, we expect to see.
Come and do your summary, and I'll type whatever is missing. Okay.
So again, we're trying to capture discussion comments or ideas that aren't in the presentations. We have all that material. So, so the basic issue of the EPRI 2003 models are
13.
Consider 13. I'm sorry, that they're giving us both the ranges and centers, so that we can use them as a proponent model just as one value, but actually a whole suite of models. The range right now is a backbone approach type of a model, with the backbone being, or scale factors, different for different magnitudes, distances, and frequencies, right? That's the way we characterize it. The way that we're thinking of doing this would likely lead to models in between there, so they'll have different magnitude and distance slopes, and not an enveloping approach as what was used here. But the centering of the model, so part of the discussion, would things move compared to the EPRI center if those were similar to the USGS? I think we discussed a bit, if you're centering somehow on data, like stress drops of magnitude 5s and things like that, anything data-driven is going to be impacted by our assumptions of the site terms. And errors in the site classification that we talked about over the last couple of days will get into that or have an effect. So if there was a systematic shift or error in some of those site classifications, that would show up, for example, in the stress parameter. That's where it will get mapped into this whole thing. So that is an issue as to why
potential differences.
Yeah, differences, and in our centering, we really need to pay attention to what that is. So from Chris, there's several different things we could use from what he presented. The MMI data above magnitude 6 could be ways we could try to constrain I put here reasonable behavior of the models as they go out to 1,500 kilometers that Bob was talking about. They need to go to be reasonable out there, and at least there's some slope that we can check against, and some way to compare with the scaling at the large magnitude, with all the caveats of what comes along with using intensity data. You kind of use what you've got. Chris's model was a simple form that didn't include the hinge. Gail noted that that just might be something you wouldn't see in the PGA data, but might show up at other frequencies if it was looked at. We asked him for 3 additional plots, just to be clear. I think to cover what Yusuf had talked about, magnitude scaling in the models, comparing it to, as it goes from small to large magnitudes using the intensity data, how that compares to the scaling in other GMPEs, and what is the scaling with VS30. Right? So we can pull that together. That would help us understanding the model. His sigma is using a constant value, and so we just have to keep track that that's going to be sort of a magnitude 4 number if we're comparing to other regions. Anything else on Chris's model? Annie.
Thank you. Hi, Annie Kammer, peer visiting scholar. One thing that Gabe mentioned that I think is important is because the empirical data only went up to magnitude 6 and it was the intensity data beyond that, there was some inconsistency between the magnitudes that were used in the CUSSC and what was shown, and I think it would be beneficial to have consistency there since the NRC did do work with Sue Huff prior to CUSSC, and then of course it went through a SHAC level 3 process.
Okay, so the high magnitude scaling right now is based on what Chris has used for those magnitudes, and we should see that they're consistent with the other studies. Anything else?
Okay, just...
There's only a handful of big events that we have.
It was Gabe's comment, so he could have kept the mic, because I know he likes it. But, specifically just making sure that the magnitudes that are used, because I think the scaling may have been for the PGA, but the magnitude that goes into the...
Chris, on that, did you check with Sue Hoff's assessment?
Well, specifically how it was processed in CUSSSC, and how it came out of that model.
Chris Kramer. I haven't rigorously checked it. I've been involved in looking at all the assessments in the paper that's almost in press, and these are more consistent with the older assessments than Sue's. I have used Sue Huff's data in these assessments. In this initial cut, I just used what I thought probably with some bias was the best estimates.
Does that capture? Okay.
So the EPRI CUSSSC has a wide range of magnitudes for sorry, when you get old, you make mistakes.
Okay, so what you're saying...
So there is a wide range of magnitude estimates. There is a central value, but there is a wide range of estimates for
that is probably, your point is that it's probably captured by Chris's estimate?
But
there's 2 parts. So Chris's paper will go out as it is. When we're trying to evaluate the magnitude scaling, we should look at the address the uncertainty in those magnitudes for what the range of the scaling is.
Yeah. So there is a range of magnitudes coming from Sue Huff and a number of other Bakken and others have looked at it. So that range is in the CUSSSC model, and we can certainly use it for an evaluation of what that does to whatever Chris has done.
So you could push it up or down and then see if that would change your conclusion on the magnitude.
Right.
Bob, does that capture what you're...
It may reduce the drop when you add the intensity data, because I think those magnitudes were generally higher that were shown, which would mean that the attenuation has been greater.
I thought that's what it said. Okay. How do you want me to write it? This makes sense to me, but...
For evaluating magnitude scaling, from intensity data,
comma,
conduct sensitivity using the uncertainty and the magnitude estimates of the historical earthquakes. Does that capture what you're trying to get at? No.
You should consider the uncertainty, but also I think you should use the same values that were used there, and that way you get inconsistency. So if there's an error in the CUSSC model, it cancels out. And when you use the two together, there's internal consistency. So it's two issues. One is the uncertainty and how that may affect the scaling, and the other is consistency.
Okay, so let me rephrase this.
Don't rephrase it yet, but I think there are two separate things we're talking about.
Okay.
For understanding and comparing the magnitude scaling in the east versus the west, we want all of those uncertainties in there.
Yes.
For centering a model for application to the east, it should be consistent with the SSC magnitude.
Okay.
Right? Those are two different things.
Why don't you type? The reason we did this switch is that usually I type better than he does. Oh, no, but either dictate or type. Okay. Yes, Professor. You dictate. I just type and I'll delete the rest afterwards. Let's start with
for comparing magnitude scaling between east and west. Isn't it 100 words a minute? You can.
No, I type with two fingers. Okay, I'm not fast. Okay.
Consider the uncertainty in the magnitude estimates of the historical earthquakes in the east. Right, that's one part.
Okay.
Second part, the model should be centered on large magnitude scaling based on magnitudes consistent with the SSC. That got it?
Agree.
And I delete the rest.
Yeah.
Party time.
One related issue. Does it make sense to limit the distance range for those comparisons? Say, don't go beyond 500 or don't go beyond 1,000?
I think we'll be doing a couple different distance ranges. One will be a shorter one, and then the other is how do we just constrain magnitude 8s at 1,000, probably there.
Well, that's what you had in here.
Well, I think the issue is we need to look at the effects of data truncation, because intensity data itself will be truncated because you'll have sites that didn't feel it, but they didn't report they didn't feel it.
Yes. Okay. So
just put a note there. Issue of data truncation at large distances.
Chris Kramer, that's an issue we address in the paper. It's an important issue, and may not be addressed enough in the paper, but it is.
It's addressed.
The way we did it, we feel we handled the truncation issue a lot better than other ways.
Okay. All right, that looks fine. Anything else on Chris's model?
okay. Summarize.
Next.
Okay.
So for what Vladimir showed, I think we need to be clear what he's doing. There's been sometimes some confusion in terms of what he's trying to get at. So I was just repeating what we said here. His reference, attenuation shape, is really intended to capture both geometrical spreading and the pseudo-depth scaling, and he does that using the form that comes out of a 70% damped oscillator. That's not critical, it's what the shape is that comes out and how he scales that with magnitude, for example. Constraints right now on the magnitude scaling are based on EPRI, but he'd be needing to bring along other information to start to do that, take that. Aleatory variability right now would be adopted from other regions. The next one, for Vladimir. So he's still going to deal with uncertainties. Site correction is not there, but the bottom one I think is the summary for what Vladimir was asking about, that we are moving towards weekly calls over the next 3 months. So don't volunteer unless you've got time. To share interim results and data with everyone who is interested, all those developing GMPs, such that simulation data as it's done will be put out and made available to everyone, and we can then also do comparison of interim results to sort of check each other's models as we go along.
That's not just for Vladimir, by the way.
That's right. But he was the one specifically asked, and this is addressing his concern.
So we're making it public, yes. The information is shared.
Then why don't you run through these?
Well, this is just the notes on the hybrid empirical method. So it's variable approach, host issues, and assumptions preserved when adapting to targets. And of course, shapes may not match. So those are some of the issues, but all is summarized really well in Ken's presentation. Youssef asked that, well, it's not relevant at this point, that provides magnitude scaling summary with comparison with other methods. The misfit currently there's a misfit in the seismological models between the hosts, the older Western U.S. model and the new SENA models. Practical limitations in schedule availability of seismological models won't allow for Campbell HEM in NG's project, but this will be addressed after the project, is my understanding. Others are welcome to try that implementation. I think that as part of the pure NG's approach, we really wanted to have a model, at least one hybrid empirical covered in there. New models being completed now that can help address those issues of the older model, including some that are both for East and West coming out from Atkinson's group. Yes?
So will there be a new HEM model being considered in NGA East 1 based on maybe on what Gail and her group are doing, or will there not?
Maybe from Sharam, I don't know. We'll have to see. We would like to see that happening.
So you have 3 months.
3 months. So this, yeah. So we'll try.
Again,
is the short answer.
Again, it's one of the models in the mix that should be. Well, ideally, you want to have it. I understand.
Well, we have it from the other models, so if no new ones are developed, we'll bring the old ones along.
Okay. Yes. So the PZESH 11 is going to be in the mix anyway. So we're not sure we're going to be able to create a new HEM model from the new data sets and seismological models, but these will be evaluated. Right.
So that was Ken's recommendation. If you don't have new one, at least use the old.
Yes, yes. So we have, at minimum, we have those. So that was a quick summary on that. Quick summary on the NGS models for standard deviation. Linda is leading the Sigma working group on that. We were using the CSS approach, the partially non-ergodic approach. So Sigma SS, of course, lower than the Sigma, but requires adding back the delta, the phi from S to S in a forward sense. It allows us also to remove those side effects, so that's really convenient. From a really quick overview of the data set, Linda noticed there's only 5 earthquakes with less than 3 recordings, so generally the events are well recorded. We do have an issue with many stations with less than 3 recordings that don't really allow us to estimate the delta S to S and phi S to S. Although 3, because you're using the full mixed effects instead of doing that as an average after the fact, we can live with 3 records at a station. We need to check the sensitivity of the CSS for that number of stations, so that's something that Ken brought up. The approach then is to compare the NGS tau and phi models from those of well-populated data sets where they overlap to adopt the larger magnitude models with the caveat that Gabe brought. Of course, we'll look at what we have in the East as well. Numerous data sets and PSS are available for different regions to provide information on the magnitude distance dependence. Most of the overlap from past results from what Linda reviewed in the CINA magnitude distance data sets is from California and Taiwan, so that's probably those that we can adopt because we have this overlap to check. Mineral and Saguenay have larger magnitudes and largest phi, so of course we're going to consider that. And there may be data issues for those earthquakes, so we need to check that it's not just the data itself that has an issue.
I have a suggestion.
Yes.
For documentation later on, maybe you just have to list the action items that we know what we have to do.
Yes.
Later on, you don't have to do it now.
No, yeah.
Or highlight it.
Yeah.
Okay, very good.
These are the action items here. This one and this one here. So, yes, on that. No, that's fine.
Linda also said that this project is going to compute ergodic sigma as well as single station.
Okay. Yes. Yes.
Okay.
To also provide ergodic phi and sigma. Yes. Okay. NGS models for
one issue of that,
yeah.
Gabe, is do we try to remove site classification errors from that? Because it really shouldn't have errors in there. So that's one way we could try to get that more applicable to what it's trying to be dealing with. I think if we just throw it in right now, you're getting a bigger one that's partly measurement error as opposed to what we really want.
I think you should. Maybe for the sigma work, you may want to limit yourself to the sites for which you have some more confidence.
Right. Can you put something like that? Consider, subset of the more reliable sites.
Or
there ain't that many.
Does that capture what you wanted here? Let me go bigger. So the project to also provide ergodic phi and sigma need to be careful with site misclassification would help to provide corrections or identify more reliable subsets for those phi. Is that it? I'm sure Norm wants to rewrite that.
Say remove measurement error, site measurement error from the ergodic phi.
Okay, that's fine. Well, it's actually classification errors, right?
That's fine. We know what that means.
Yes. You see, I'm not any better than Norm in the end. Classification. Yes, careful. We have to fully be careful. Okay. So those are the action items related to that. And then the other things, this is just more a note on your epistemic uncertainty. I don't think we need that here. Additional issues to consider, spatial correlation, I put no, not for NGEs, but we need to consider the fat upper tail issue, and that's something we'll address more in workshop 3.
Upper tail, you need to write show sensitivity to fat tail versus standard model for the October workshop.
I know, I saw it.
Hazard sensitivity.
Hazard. There was no microphone next in here. Be it standard model or normal model. I really didn't hear.
We should declare victory and have a comment.
Actually, can I say one question that I could not understand yesterday? In Jason's presentation, the code 4 sites were the ones that showed the least cutter. Is there a good explanation for that?
No. So we're sending that back to
the Geotech Working Group.
That's our feedback for them to figure out what's going on.
Okay, so we're at the observers' comments. Jim Marone?
Yeah, Jim Maroney, observer. At an earlier workshop, there was some consideration being given to vertical motions. What's the status of that?
This was removed from the official SHAC, the NG's project. Yes.
Okay, and there's no other task group working on that?
It's out of the scope of SHAC, but parallel to that, under west and east and so on, we are going to do something about vertical, but it's not part of our scope.
Okay, thank you.
It's not part of the scope that we try to finish in 3 months or 6 months.
Sure. Okay, thanks.
Okay, is that it? Observers, that's it? Oh, then Larry.
Where is Larry?
Larry Salamone, Joint Management Committee. A good closing statement would be just to summarize the schedule. We've heard 3 months and then 6 months, for certain activities. Could you just summarize it one last time as a good way to close the meeting?
Yes.
There's going to be a couple of observer comments from the online that I was looking at. Yes, Larry, I missed that. Sorry. Can you repeat?
Oh. Yeah. Just perhaps a good way to close this part of the meeting would be to summarize the schedule of the technical activities.
It's in. Well, I cannot promise to do that. It's somewhere on this computer. I don't know where. Bottom line, I can summarize in words. You can look at the presentation. Workshop 3A is October 29th, 30th. Okay, this has been on the website for 8 months at least now. 2014. Then workshop 3B is January 21, 22nd, 2015. The wrap-up meeting where we present the final results is April 13th, 2015. And we're working through documentation as fast as we can through that so that we're done within a few months of those dates.
Yeah, I had personally, recorded those workshop dates. But what I think might be helpful is when do you expect to complete the technical work, have the GIMPs, to start doing the hazard, sensitivities, and then start the report writing, which, should be an ongoing process, but...
It is ongoing, and you will see the first set of results that we'll share publicly with the project people at the workshop in October. So this is an ongoing process, yes.
So observers on the line?
Yeah, there was a couple observer comments. Can you read that? Maybe you can give her the microphone, or... Yeah. Thank you. Just state who and read that out, please.
So the comment is from James Bella. It's on clusters/10. He says clusters introduce a bias, averaging all the models. By contrast, samples the full range of knowledge, and the end result may be checked against actual earthquake ground motion records.
So we are not using clusters partly for that reason, to avoid trying to put what are basically merit weights on the different approaches, and So through that process, we will have a continuous distribution of the ranges of the GMPEs, and the issue is centering. That's what this is all going to come down to. I expect that the range that's already in the EPRI NRC models there will be similar to what, they've already got a substantial range, so we'll probably be capturing something like that. But that's one reason we're going to this Salmon's map approach, to avoid that issue of having to put merit weights on the clusters approaches. Bob is shaking his head yes, so that's good.
Okay, so on Chris Kramer's presentation, if you entered the historic intensity data on USGS, did you fill it unknown event website? What kind of useful information might that generate? Useful information might that generate?
So Norm, that ties back to what you talked about a couple of days ago, that Dave Wald wants to look at the intensity data.
So Gail has done some of this and working with Dave Wald. So Dave Wald also at the USGS has agreed to work with us to bring all that did you feel it data into it, so we can try to see any constraints that provides on the scaling of the ground motion.
Yes, and that includes also recent work by Suhoff on the potential bias of those data. So that's part of the USGS. Yes.
The work I did that's in this paper is on older MMI, true MMI, not CII data, for the most part, and so we're kind of avoiding that issue.
Okay, that's a good point. Thank you. So is that it? Do you have two more comments?
Okay, so on Grazer's presentation, UK has a lot of earthquakes within the range of the SENA database. Perhaps some information on their ground motion attenuation curves would be helpful.
I'm not sure I understand the question.
It's not a question, I guess. It's just a comment. Yeah.
So we'll copy paste. We'll email Vladimir with that comment.
Where is that one?
No one needs new glasses.
I'm old and I can't see that far. No, it has to be the right.
There's a distance attenuation in his eyesight. Age proportional. Sight effects. That's good. Sight effects. We're having too much fun.
Okay, so I think all they're trying to talk about, Vladimir, is seeing more of the details of the model and how it's fitting the CNA data as opposed to comparing it to the EPRI model. Because that's what you were showing in some of your comparisons were more model to model instead of model versus your model versus data. That's all that they're talking about.
Okay, thank you. And that's it? There was one more.
Okay, so this is a long one. The shape of the response spectra should reflect or track consistently with the that would be the magnitude, I guess, magnitude of the earthquake. Large earthquakes have large slips on large faults and more energy at longer periods. This should probably be a physical constant of the model. By
We agree. Okay, that's what I realized.
By analogy with the West, you cannot force large earthquakes into a long normal distribution. Large earthquakes more correctly reflect a power law distribution with fat tails. And these do not allow meaningful calculations of median values and standard deviations. Do you see any effect on ground motion attenuation reflecting A, geologic structure, B, presence of active seismic zones, C, velocity models, or crustal thickness?
And I think the way we're going to address that is with our simulations. So that's really, I think, the answer, the finite fault simulation with the good and bad of what's in the kinematic models is as far as we're going to be able to take that kind of an effect and its evaluation.
And the other part is addressed through the regionalization. Okay.
To the person, I know who wrote that, and we'll respond to him in a little more detail later on.
Done, right? All right, very good. So officially, this is the end of NGA East 1, workshop number 2, SHAC level 3. So we have 1, 2, 3. Before we leave, I wanted to thank again sponsors, NRC, DOE, and EPRI. I like really to thank all speakers, resource experts, proponents, observers. It was a fruitful 3-day meeting. Especially I'd like to thank TI team. They spent lots of time, especially Norm and Christine. They really spent lots of time for their dedication and efforts. Peer staff, Yolanda, Stephen, they spent lots of time on the background and work. And finally, peer volunteers, Sifat and Sahar, 3 days hard work. Appreciate that. So thank you very much, everyone. We'll see you, all of you in October. This is the end of the workshop. Thanks a lot.
Yeah.